algebra or something like that. So I'll be discussing that. Before that, I would like to know, you're all faculty and students. Have you studied linear algebra or matrix theory or equivalent courses in your during your engineering, or many of the teachers or faculty you might have been teaching that course? So I want to know what is your background. So what was that course?
So it was matrices, transforms.
Okay. These people, these are all students. Have you undergone any course on?
We had subject on
What is that?
mathematics in that algebra, mathematics.
Okay. If I ask you per se, just throw a word, basis, you understand? Okay. Fine. So I think here and there you have some basic knowledge about linear algebra, etc. things. But I would like, before I start something, I would like to say certain things. What we call linear algebra in math perspective. In engineering perspective, it is like linear system analysis equivalent is that. So linear system analysis is a very fundamental for engineering, but linear algebra may be for science and other backgrounds. So it becomes so fundamental that we must undergo that course. If you are a faculty, some point of time you have to teach that course. If you are a student, graduate student, rather undergrad, so that you have to undergo that course, because that's very fundamental. That becomes a fundamental for nonlinear theory. So, and I used to say my students, linear algebra or a linear system analysis, there is only one linear system theory. What I mean to say is there are varieties of nonlinearities. Okay, so the linear system theory, if you apply to hydraulics per se, or electrical engineering, or mechanical, or anywhere, the same theory is there. That is tuned to the background of whether domain of mechanical, electrical, etc. things. So in that sense, the theory is well developed, and linear algebra, linear system theory is very nice and very beautiful, rather, in the sense, if you start reading linear algebra, it is so nice that you continue reading that because it is highly structured. We say wherever structure is there is beauty is there. Beauty in the structure, like. Okay, so it is not hard or difficult to undergo or understand the concepts of linear algebra and linear system theory. Certain remarks I have to say. In our engineering, we study signals and systems, probably electrical engineers, in the third semester or so. So in the third semester, that becomes more of a functional analysis rather. So without studying the fundamental matrix theory and linear algebra, we directly jump into the functional analysis type of a course. So that may not be correct, and we have to undergo in the discrete space, etc., matrix theory and other things before we jump into the continuous functions and function spaces, like. So that's the one thing. And as Professor said, I learned a lot of mathematics when I was in Indian Institute of Science. I have to be grateful to that. I would like to thank and acknowledge Indian Institute of Science for that, because it provided, rather, we learned a kind of research culture and academic culture there. So that's why it is a very great institute, because nowhere in India you find such kind of a culture. Okay, so that's another point I would like to mention here. Okay, so how to start this one is a problem, like. It's a way to start, like, because certain background, but for me, okay, I'll start somewhere like from the high school level. You have studied something like algebraic structures. I don't do too much of maths in this, but I would like to say very intuitively what it is like. Okay, everything starts with set. Okay, we understand what set is. Usually it's a non-empty set. Non-empty set, it gets a structure. Mathematically, structure means what? It satisfies certain properties. Okay, certain properties. A set satisfies certain properties, it gets the structure. So the algebraic structure is like that only. Yes, a set, non-empty set with certain properties. If the certain properties are depending on the structure, you call that as a group, vector space, rings, fields, etc., etc. It becomes more of an abstract algebra after that. So we have studied in the high school group structure. The sense given a set, okay, you all understand the set of numbers at least. Okay, set of numbers. What are the numbers? You have to interact with me. Tell me the number sets.
Real numbers.
From the very primitive. Natural numbers. Natural numbers, somebody will include 0, somebody will exclude 0. There are other things like that. After that, integers is there. Integers, rationals, irrational is there, reals and complex. At least until complex we can study that. So all these are infinite sets, right? So we do set operations so that we say this property is satisfied. Usually in the group structure what we take is a binary operation. Okay, binary operation could be anything, right? So binary operation, we take two elements from the set and then do the binary operation. Per se, G is a set, non-empty set. G is not equal to 0. I write in this fashion. Suppose A comma B from the G, you do binary operation something like this. And the result, per se it is C. C should belong to the G. Then it is called closure property, etc. things you know. So like that, so we have binary operation, and you can do various, we can check various properties here, probably like closure property, associative property, all these you know. I don't want to go very elementary level there. Closure property, associative property. One more is existence of identity element. What is identity element? Per se A is there. To the E, it becomes EA to the, this becomes A. This is your identity property. And you know that for a set, identity element is unique, like. That's the one thing. And another important is the inverse of each element there. Inverse is unique for particular element. So each element has inverse. So we call, with respect to that binary operation, that is the inverse, okay? I write something like A inverse here, okay? A inverse is E. This is a property, okay? So a non-empty set with these properties called, it becomes a group, okay? So group. You can immediately, once we define group like this, we can give examples of groups, etc. The best example is a real, because real is a highly evolved number system. So by default, it becomes the answers to many of the questions. Okay, what I would say is you have to identify a very primitive set where it is just a group. Okay, like that. Okay, you can think. Fine. Once group is there, so okay. Before this, you can have monoid, etc. structures. Let us not go into that. At least we understand what group is. So next is, everybody, you have heard of vector space, right? Vector space. Mathematically, you can denote this as G with an operation here as a group, like. Okay. So in the vector space, we need two binary operations. Usually we call vector addition and scalar multiplication. Okay. So vector space, again it is a non-empty set V with two operations, this and this. Now with respect to addition, you can check these properties. With respect to multiplication, you have to be a bit careful here. Okay? And there is an interplay between addition and multiplication. Okay? So vector space is a group with respect to addition. I define group here. I take this definition. Vector space is a group with respect to addition. So it has additive, identity, and inverse of each element is there. That's why we talk about zero element in the vector space and negative of an element in the vector space. That is with respect to group. The next one is this one, scalar multiplication. Usually the scalar, if I say this, scalar is from the field, okay? They call field. Usually it is vector space over a field. Field is another evolved algebraic structure. We will see what field is. Okay, fine. So there are properties, 4 or 5 properties with respect to addition, 2, 3 properties here, and there is a distributive property which includes both plus and dot. Okay, so it could be left distributive, etc. Associativity with respect to scalar multiplication, those properties are there. So any standard reference you will get that. So what I would say is vector space is defined over a field or on the field where scalars are from the field and the elements x belong to V. This is a vector from this. Okay. So vector space has a group structure hidden, okay, inside this. Okay. Then there are other structures which is bit evolved than these rings, etc. Let us not go into that. But I just say here field because we use this, because vector space over a field, like we say. Okay. Again, I go back to the group. Okay. So field could be F is a letter for me. I use that letter F is any set, non-empty set. Again, it has 2 operations, this and this, addition and scalar multiplication. F plus dot. I have to be a little bit careful here. I can change this notation to V plus F dot usually. Let us not too much bother about mathematicians' notations, but the notation is very important because notation takes you further. That's how it is. Matrix is a very nice notation rather. Okay. So this is the plus addition is with respect to this, dot is with respect to F. So this is a field. The first one is F plus is abelian. Abelian means commutative group. Commutativity, you know, A binary B is B binary A is commutative property. So F plus is abelian group. Second one is F dot is also abelian group. Here when dot is nothing but it is multiplication, since it is a field, here it's a scalar multiplication. Okay, A into B, like that. So one thing here is this has additive identity and in additive inverse with respect of each element. Here you have multiplicative identity and as well as multiplicative inverse is there. Suppose I take a number 7 on the reals. What is the additive inverse of 7? Minus 7, because 7 plus minus 7 equal to 0, where 0 is the additive identity. Right? So what is the multiplicative inverse of 7? It is 1 by 7 because this is 1. This 1 is the multiplicative identity in this one. Okay. So, but when I have to be a little bit mathematically careful when I say this one. All non-zero elements have multiplicative inverse. That's the one. Otherwise, you'll ask a question, what about 0? Like 1 by 0 is, it is undefined. Like. Fine. So this is a field. So field is more evolved than vector space. Okay. So, but anyway, we deal with vector space, which is very nice structure. So vector space means it has 2 operations plus and dot. Okay. So this is kind of a definition for. This is with respect to general mathematical object. We will see some examples for vector spaces. Okay. So the first thing is vector space is a non-empty set with binary operations. Okay, that's all. So now I'll ask you give certain examples of vector spaces. Give me some number sets which are vector spaces. For granted, you can take field as real field, right? Okay, probably one more thing I'll just say here. The arithmetic operations, these are there. Addition, subtraction, multiplication and division is there. You can ask the question whether can you do all these 4 operations on these structures. Okay. So here you are defining addition. Okay, binary operation is, if you define this binary operation as addition, probably additive inverse is there, so you can do subtraction. There is no multiplication, otherwise you have to say G plus G this. Okay, you have to consider group structure with respect to this, group structure with respect to this. That may not be, unless otherwise it is. So vector space, you have what? You can do addition, subtraction. Can you do multiplication? Is multiplication of two vectors defined in the sum? Maybe you can have element-wise definition and all, but suppose if I have a vector per se, before taking example, I'm saying the example here itself, you know the tuples, right? RK. RK means, you know, RK is, what is RK? Everybody understand RK? Okay, you don't understand RK. Fine. What I mean to say, I'll come to that. So what I mean to say that you can do scalar multiplication, not the vector multiplication here. Only scalar multiplication. That means you take a vector x which is in V, you can take alpha which is in field, you can do alpha x, that's all. This alpha x belongs to, again, the V, closure property. But you cannot do to vector multiplication here. So when you come to field structure, you can do all four operations. Okay, you can do addition, subtraction, as well as, because there's a multiplicative group is here. Okay, this is a abelian group with respect to multiplication. That's why you are doing all this in the reals. They're on the reals. So 7 minus 7, 0, and 7 plus 0 is 7. And 7 into 1 is 7. 7 into 1 by 7 is 1. Okay, like that. So it is there. Fine. So let us go back to the vector space. Any question here? So the summary is, all these algebraic structures are defined on non-empty sets and with certain properties. The properties are like, with respect to a binary operation, right? It could be usual closure property, associative property, existence of identity element, inverse of each element, commutative property if it satisfies, like this. Okay. So that's how you check the structure within the set. You just check the properties. If it satisfies, okay, that set gets that algebraic structure, like that. Okay, this is more algebraic way of saying this. There's a geometry there, right? Okay. So in geometry, I mean, we have more subjective feel for geometry than algebra. Algebra has more expressions, polynomials, etc., things. But our feeling for Euclidean geometry, plane, lines, are probably we have more subjective feeling for that. So we'll interpret that in terms of these things. Okay, so I'll just erase this. Okay, so let us go one by one per se set of real numbers. Let us understand Euclidean space first. You know, real line is this, right? There is some zero here. This goes to plus infinity, this goes to minus infinity. You can have numbers on that. Okay? This real, this is called a scalar. If you want representation, per se 1. Per se 1 is a vector notation here I am using. Next is R2. What is R2? R2 is plane. You can call this x-axis or a y-axis, certain things like that. x1, x2 or whatever it is. This is the origin. Okay. You know tuple notations. 1, 1, 2 belong to R. 3-dimensional is, you know what that is. If I write 1, 2, 3, R. Okay. So these are very standard because, as I said, real number is highly evolved. You can have most of the structures. Here I say this is R1 because that 1 stands for something like dimension. We'll come to that. Okay, fine. So this is how the geometry is: real line, plane, and this. If you take any point on the real number, it is a vector per se. It could be 1. If you take any point here, you have corresponding and x and y, maybe 1 comma 1, like that. So every point in your classification, you say every it is a d-dimensional feature. It's a d-dimensional space on which you put that point. It becomes a scatter plot, like that. Okay, like this in R3. So that you can do vector addition, scalar multiplication, not like this. You cannot have 1, 2, 3 into 1, 2, 3 like, unless you have your own definition and consequences of that. Otherwise, it is meaningless like. Okay, so this is not that. Okay, fine. In the vector space, there are like your feature vector and all these types of structures are very common. Like you have 100-dimensional features. They lie in 100-dimensional, probably Euclidean space. Okay, once let us go. Okay, so there are certain concepts notions in the vector space. We have what is known as linear combination, linear independence, linear dependence, linear span. A fourth one is basis. Fifth one is dimension. Okay, so you have heard of these keywords at least, right? What is linear combination? Okay, per se you have vectors x1, x2, x3 in some vector space V. Alpha 1, alpha 2, alpha 3 belong to the field because this is a vector space over the field. You have alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3. This is linear combination. Okay, alpha can take any real value. There's no restriction like otherwise it's convex sets and all, there are restrictions. So here it is no restriction. So this is linear combination. You know that linear combination is closed because it becomes another vector in the vector space, right? Okay, how many vectors are there in a vector space? How many? So many it is. Infinitely many, like, right? Infinitely many vectors are there. Per se, for an illustration purpose, I write something like this. This has some Rn. I'm not putting the boundary there just for illustration purpose. And there could be a vector here. It's one point there. There are infinitely many vectors there. Infinitely many. Including zero vector. That's more important. Okay, the one requirement for a vector space is zero is there. Zero is everywhere, like. Okay. For example, if you substitute alpha here as 0, each alpha can take 0. It becomes a zero vector. Zero vector is there in the vector space. So that is a must. For example, in your linear system theory, you say, how do you check for linearity? Okay, I had to go to the transforms here, operators. Okay. So there is zero input, like zero input. Okay, finally it gives a zero output. That's a separate, I have to talk about linearity there. Fine. Once you have set of vectors, now you have set of vectors. S could be, I can say x1, x2, x3. Now you can talk about linear dependence, independence, all those things. If there is only one vector, what is that? It is linearly independent. There is no other guy to compare it with. Suppose there is a zero vector, only one zero vector. We say by default, by convention, we say that it is linearly dependent. Okay, but it's only one vector per se. If you take, what is the use by taking that and all? We don't know. Mathematically, simply asking the question. Okay. So a set may be linearly dependent, independent. You know the definition for linearly independent. What is that? You have suppose x1, alpha 1 x1 plus alpha 2 x2. Per se, I just take two vectors. I want to get a zero vector. That means alpha j is 1 and 2, has to be 0. Then you say x1 and x2 are linearly independent, right? Suppose at least one alpha is non-zero. What happens? You get linearly dependent set. Okay, what do you understand by linear dependent set? Per se, I give you three vectors. What is your understanding that linearly dependent? The set is linearly dependent. What do you mean by that?
One is given by a linear combination.
For example, I'll give you a simplest example. You understand all this. Per se, these two are vectors. One more vector I'll give you this. This is a set of three vectors, x1, x2, x3. Okay, this is linearly independent set or a dependent set? I have to be a little bit mathematically careful writing. This is this, okay. Is this set linearly dependent or independent? Okay, I'll not go to that. I'll go here itself. 1, 2, 2, 4. Tell me. Oh, this is linearly dependent set because the second vector is twice the. Okay. Or you can say this plus this. Okay. Here, okay, twice actually the scale element. Here what happens? This vector is linear combination of this and this. So this is linearly dependent set. Okay. So, but there are other definitions I have seen. Usually I too got a confusion that in linear dependent set, my understanding was this, but I get corrected this. Any vector can be written as linear combination of other vectors. Like, is that definition, is that true? Linear dependent set is there. Our feeling is any vector in that can be written as linear combination of other, per se, two vector or whatever in this particular case, other vectors. So I got it corrected. The correct is at least one. It may not be for all. That means if you take x1, x2, x3, three vectors, it is not that x1 is written as linear combination of this, x2 is written as linear combination of this, x3 is written as linear combination of that. No. At least one can be written as linear combination. I'll give you a particular example. I don't have that this time. Per se, tomorrow I'll give you right on the board like. So at least one vector is linear combination of others. Okay, one is enough. May not be all like, it may not hold for all. Fine. Linear dependence, linear independence is over. Linear span. Span means what? Span means set of all linear combinations. I'll go back to geometry again. I'll just be in the plane R2. Per se, you know, in linear algebra, every vector starts from the origin. Beginning point is the origin, because that is how it is standardized or whatever. Okay, this is a vector. This vector is in 2 dimension. You have two components per se. This is 2 and 1 per se. How do you get the span of this? I want to get the other vector by the only one important operation is linear combination. The linear combination includes scalar multiplication and addition is that, right? Okay. In that sense, in the vector space we have two important operations. One is addition and scalar multiplication. Okay. So what is linear span here? Suppose if I multiply this by alpha is positive, maybe greater than 1, you go toward that side. Whatever the alpha you choose, right? And negative alpha you can. So the span is this, the entire line. Okay, that is set of all linear combinations. This is per se, this is x equal to this, alpha x. Alpha can be anything from the field. Per se it is real now. per se. This is a span. Suppose if I give two vectors, this is one vector, the other could be this vector. Now how do you construct linear span? Just like this only. So it is again linear combination. Okay. So suppose if I multiply this by 2, I'll be somewhere here. If I multiply this by 2 somewhere here, any scalar multiplication it will go here. And also addition is there. I can add these two vectors. You know how to add these two vectors, like tip to tail rule or whatever it is. Okay. This is the sum. I can add these two vectors like that. I can have this, and what happens? What is the span here? Okay. I can go here also. I can go here also. Okay. There are a lot of combinations possible. Okay. What is a span? Span, suppose it's the x1 vector, x2 vector. What is the linear span of x1, x2? Okay. So if x1 and x2 are linearly independent, it becomes the entire plane. Right? Entire plane. So that's why the basis definition is there. You can span the entire plane using just two independent vectors here. Okay, that is called linear span. Then, okay, we have defined linear independence and linear span. The definition for basis is told in terms of linear independence and linear span. So we know that every vector space has at least one basis is there. It might have many bases, maybe infinitely many. So what is a basis then? What is basis? Basis gives you a kind of representation for any vector in the vector space, right? It has to be represented. Any vector, given vector, has to be represented using basis vectors. Okay. So even though in a vector space there are infinitely many vectors, we don't want all infinitely many vectors. We want the basis vectors which are finitely many here. Okay. Even though the vector space has infinitely many vectors, okay, its dimension is anyway finite because it is the what? Cardinality of the basis set, we say. So what happens? This becomes a finite dimensional vector space. Okay. So what is basis then? The basis has to be linearly independent, first thing. Second one is it has to span the space. Okay. So in R2, per se let's go to R1 only. This is R1, that's 0. You know the structure in this R1, there's only one component. R2, there are two components. You have to recognize these. 1, 2, 3 components are there. In n tuple means it is in n dimensional space, right? This is just a real line R. Anyway, if I have a 0 vector, I can't do anything with the 0 vector because 0 multiplied by anything is 0, right, like this. So I have to take a non-zero vector. Take a non-zero vector. Per se, 1 point, I don't take 1 because it's confusing every time. If you 1.2 will take. So 1.2, will it span the entire line as a question? Is it linearly independent? If these two properties are satisfied, it becomes a basis for R. Right? Given 1.2, which is non-zero vector, a single vector, it is independent. Okay. The next is, I have to get the span of this. Span of this is nothing but alpha times 1.2. Right? 1.2. Alpha can be anything. Positive, negative, 0 also it can be. So substituting value of alpha, you can span the entire real line. So one of the bases for R is 1.2. Now 1.2 is a basis. You can give many examples for basis for R or R1. Can anybody tell quickly? You can give your own basis. What is the basis for R? If I say 1.2, that is all. Okay, 1.2, only 1.2 is the basis for all? No. You can give any non-zero vector. Let's go to R2. R may be very simple example. Let's go to R2. Okay, in the R2, if I just give any one vector, will it span the entire R2? It will not, because you can move along the line, that's all. Okay, if I give you another vector in the same direction, even this fails. Okay, I have to give another vector such that this vector and this vector are linearly independent so that it spans the entire R2. So those two vectors become the basis for R2. Per se, if I can talk in terms of angle formed by this vector, suppose they are having some non-zero angle and not 180 degree. 180 degree. You understand what I am saying? If I give you one vector somewhere here, another vector with an angle theta which is non-zero, but not 180. 180 means this becomes this. That spans the entire R2. The best example is your, standard vectors like this and this. This is 1, 0, right? 1, 0. This is 0, 1. This spans the entire R2. Okay. So like that, you can find basis for other Rn, Rk, whatever it is. And you know that if this is a basis, suppose this set B, B capital I write, 1.2 is my set, cardinality of B, the dimension of the space. Dimension of the space. Here I need two vectors, the dimension is 2. So in general I need n linearly independent vectors. So that becomes the basis. So the dimension of the vector space is n. Okay. But I'll test you this. We are in R. I'll give you 1.2 and 2. Set is yes. Okay. What do you say about this? Is this a basis for R? Is a set linearly independent? You check first. (1.2) and 2. Can I get 2 from 1.2? Possible. I can find some alpha which gives me this. Or 1.2 from 2, it is possible. So these two are, this set is linearly dependent set, first of all. So it doesn't qualify to become the basis. Okay. But now, this is linearly dependent. If it is, okay, we have something excess here, right? You can remove the redundancy. It's a scanning process, either from left to right or right to left, it's your wish. So if I start from left to right, okay, I first choose the whatever available vector. I check whether this is linearly independent with this. Since this is not, I will discard this. You can do this for, if the set is having many entries, you can do this. In this case, I'll discard this. Finally, I'll get a linearly independent set. It becomes a basis. That means from the dependent set, if it spans the entire space, you can get the basis. The second property is a spanning. We know that 1.2 spans the entire R. What about 1.2, comma 2? Will it span the space? Why? Span means what? Linear combination. Alpha times 1.2 plus alpha 1 time, alpha 2 times 2. I can substitute alpha 1, alpha 2 from whatever any number. And you will get some number, no? This number, some number that will be somewhere on the line. It is possible to span the entire line using this also. This also. But there is redundancy is there. Okay. So you can have, okay, as I said, for basis this is enough. This is linearly independent and spans. But if you take linearly dependent or independent and a span, this is linearly dependent, but it spans the entire R. Okay, that subtle thing is there. So but there is a redundancy, you have to remove that if you want to extract the basis. So now I'll change the definition for basis. More optimal definition I have to have now. The basis is what? Maximal linear independent set, minimal spanning set. Okay, how do we say this? Look at this here. I can have 1, 2 also somewhere here, probably this is. If you look at this example, we are in R2. We know that we need 2 linearly independent vectors to span from our whatever the discussions. But what I say is this is linearly dependent set. We know that. But it spans R2. Spans R2. How do you say about basis? Basis means there should be minimal linear independent set. Per se, the scanning process and choosing process we are saying. Per se, if I choose this one, and I'll check this with this. So this is linearly independent. So I have to include this, right? When I come here, this is linearly dependent with these two. Okay, I have to discard. Here also I have to discard. So these two minimal linear independent set and maximal linear independent set, maximal linear independent set and minimal spanning. Okay, minimal spanning, otherwise this also spans the entire R. So if I just give this one vector, it will not span the R2. So I need one more. So it is maximal linear independent from this direction, minimal spanning. Okay, so there are redundant representations in signal processing, like when you represent a signal, there are redundant representations are there. So the basis representation also, the basis is more optimal, just enough, just enough. Okay, we know the basis and dimension. So dimension is nothing but cardinality of the basis set. From this we know that there's R1, R2, Rn, Rk, whatever it is. Fine. So this is basis. Why basis? Using basis you can represent any vector in the vector space. That's one thing. But when I say this is some per se R2, if I recognize a point here, I have some coordinate for this, right? In that sense, suppose this is what? Minus, what is x? X could be minus 2, y could be minus 1, right? Minus 1? Oh, minus 1. To say minus 2 comma 1, that vector is already represented in some basis. In this case, it is standard ordered basis rather. Our standard ordered basis is what? X and y, your Cartesian coordinates. X and y, this is standard order. Standard because we suppose 3, 4 is a vector. You know, this is represented as 3. Okay, this is a scalar, this is a 2 axis. This is a standard basis. 3, 4, we recognize our conventionally. Convention is already represented using this basis. So whatever you write in the tuple form, it is assumed that there is standard order basis already. You can change the basis. You can have some other basis instead of standard basis. Suppose these two are the basis, right? In the standard basis, what happens? If you're given a point, you project here and here, you will get a xy coordinates. Correct? Suppose there is this same point, I want to get coordinates for this basis. These two are my bases, right? So I have to correspondingly project, this is orthogonal projection, right? Project onto this and project onto this so that I'll get the coordinates. Okay. So you can change the basis and represent. But our conventionally we are practicing this standard order basis, we have more subjective feeling for that. Like, okay, this is about vector spaces and their things. I have any question here?
You used R and F. How do you distinguish between them? Is it a set and a space or?
Okay.
I see.
R as a vector space and F as a field you may use. F is for field here. Field, when I say field is a scalar. Suppose I have R3 per se, R3. I take 1, 2, 3 as the entries of one vector. Each entry is from the field only. Okay, field only. And if I do alpha times this, alpha is from the field in this case. Alpha is from the field. But there could be differences. For example, I can talk about R. The vector space is R. The field may be, okay, I have to be a little bit careful. I'll put vector space as complex. A field could be real. Is it possible? To be a little bit careful here. Field is, scalars are from the real, vectors are complex. Okay. Or the other way also you can think and appropriately you can answer that one. Maybe set of all rationals. Rationals if I take, right? Rationals are vector space. Rational means what? A by B. A by B is a set of all rationals. I can have a negative of that is possible. A by B, identity, everything. Rationals are vector spaces. Correct? Set of all rationals. Now, rationals over the field. Okay, is rational a field? Okay, first I have to ask that question. Is rational a field? Yes, it is, because there is multiplicative identity, multiplicative inverse, everything is there. Rational is a field. Before you go to real, rational you get. Rational is a field now. So, now the vectors are from reals per se. Scalar is from rational. Or vectors are from rational, scalars are from reals. You can check these combinations. Usually, by default what happens is, we take from the same field, default is real, the entries are the real entries here. Otherwise I have to talk about rational or a specific integer kind of a cases. But that might not. So, by default we take both as reals in this case. But such questions can be asked, it's nice also.
So the alpha 1, 2, 3 could be said to be either from F or R1.
By default, R1. That's nice observation. So something could be a vector space over, usually suppose n tuples, or vector space over reals we say. N tuples may be vector space over some other. Okay, I have to be a little bit careful in making that statement. But there are examples of that. The field is different, the vector elements are from the different like. But both are fields like. If I take rationals, rational is also a field. Reals is also a field. Vector elements may be rational. Scalar may be real. Okay. Fine. What I was saying then? Any question? Any other question? One more thing I want to say here is this linear algebra or whatever this linear analysis you study, this is irrespective of signal processing or image processing or your medical domain or something else. This gives you more analytical ability to deal with your research and other things. It should be like in our when we were very kids and childhood days, our parents used to teach 1, 2, 3, 4 weekdays. It is called by heart, by pata and all we used to call in Kannada. Okay? It is like that now because you should know linear theory. So it gives you more confidence and more structured language for representing other things and posing problems. Okay, it's like that. So it's very fundamental. So linear theory is well established. You should know linear theory, whatever the domain you are in. Okay, that's the one thing. The second thing is vector space structure. I'll just put these objects. Okay, what is this? This is scalar. Okay, I'll write something like this: 2 tuple. This is 3 tuple. R1, R2, R3. I can have Rk in general, right? Rk. Rk is a vector space over R. Next, I can have, this is a vector, I can have a matrix. In general, set of all matrices over Mn. Matrix elements from the reals. So, set of all m by n matrices is also a vector space. Right? You can add 2 matrices, the result is another matrix in the reals. You can have a scalar multiple of a matrix, so it is also closed. So set of all real matrices of m by n forms a vector space. So what is the basis for this and what is the dimension of this? Okay. We talk about structure and other things. Suppose 1, 2, 3, 4, in many of our signal processing operations we make this as a vector, right? 1, 2, 3, 4, like 1, 2, 3, 4. Okay, the same structure is preserved actually in the linear algebraic sense. This dimension is Mn. Here it is 2 by 2 into 2 is 4 dimension. How much? Okay, if you know this representation, right? Basis representation for this. Quickly, if I use standard basis, what happens? Wherever that element is there, you make this. So what is the cardinality? What is the basis here? This one, this one, this one, this one. Cardinality is that 1, 2, 3, 4. There are 4 elements. What is the dimension of this? 4. In general, it is Mn. So these are all one type of math objects, if I call. Mn matrices are another type of objects. Next, I can have what I can have? Polynomials. Over reals again. So if I write a0 plus a1x plus a2x square, it's infinite polynomial. Okay. I can make this finite plus this is something like an x to the n. So I stop this. It's a finite degree polynomial. Now, set of all infinite degree polynomials. That's also vector space. Set of all finite degree polynomials, degree up to per se d or n, degree n, up to n. Okay, d used for dimension, I'll use this n. If you take set of all polynomials up to degree n, it includes all the polynomials of degree less than n also. That is a vector space. If you consider just set of all polynomials of degree n, it is not a vector space. Not a vector space. Okay. Can you identify the 0 element here? A negative of an element? What is 0 element in the matrix case? What is 0 element here? Let me just ask. What is 0 element in R3? Origin in R3 is 0, 0, 0. What is origin in 0 in here? 0, 0. What is 0 here? 0 here. What is negative of an element? What is negative of 1, 2? Minus 1, minus 2. Negative of this, minus 1, minus 2, minus 3. So we identify 0 element and negative of an element. That's a group property. I ask you the same question for matrices. You have 0 matrices, right? Negative of a matrix is possible. So 0 element and negative of an element. 0 polynomial. 0 is a polynomial. That means p of x is any polynomial plus 0 and negative of a polynomial. I can take minus of this, no? Minus of p of x. Each element is negative of a polynomial. So that what happens? P of x plus minus p of x becomes 0. That's what it is. So polynomials is a vector space. Okay. Polynomials is interesting because its dimension is finite if I just restrict until n. Okay, what is the dimension? Okay, I'll just take this example. 1 plus 2x plus 3x square per se. It's a polynomial. So of degree 2, up to 2 it is. It's a one element I am writing. So this is a set of all polynomials of degree up to 2 is a vector space. What is the dimension of this? For dimension I have to have the basis for this. Basis are monomials. What are monomials? X to the 0. What is that? 1 into x to the 0, 2 into x to the 1 plus 3 into x to the 2. Okay, you can extract this. 1, x, x square, etc. Whatever the degree you want. That becomes the basis for polynomials. I can have finite dimensional polynomial space. What is the dimension of this? Where this polynomial lies? Which dimension? Or what is this is there? It is degree 2. It is in 3-dimensional because this is also there. So that's why this is equivalent to, this is an element in R3. We talk about isomorphism and etc. things like that. So polynomials, a finite dimensional vector space. But if your polynomial has a continuous function, it's a function space it becomes. Okay. So we have seen polynomials. Next is sequences. Not sequence. What is that? Sequence. What is sequence? You know, it's a discrete signal like. You can have 1, 2, whatever, converging, diverging, whatever this is. It's the extension of a vector. Finite vector, infinite sequence. Set of all sequences is a vector space. You can add 2 sequences. You can have 0 sequence. You can have negative of a sequence. After sequence, you have continuous functions, set of all functions. Okay, f of x and g of f1 of x, f2 of x, take 2 entries from the functions. You know how to add 2 functions element-wise. Even though they are continuous functions, our thinking is when adding point-wise addition. You can add 2 functions. You can have 0 is a function and negative of a function. All is possible. So we can, okay, like that we have to see. This is in the case of finite vectors, matrices, okay, polynomials of infinite, okay, and then finite degree. Many polynomials we use interpolation, even our regression problem is polynomial fitting only, right? Then sequences is one side it is infinite, right? Okay. So sequence is a vector space and set of functions. Still you can classify subspaces, etc. But generally I speak, set of all functions also form a vector space like. So that you can add 2 functions, negative of a function, etc. you can do. And finding basis may be a little bit tricky in finite dimension. Okay, whatever the vector spaces here, they are all finite dimensional vector spaces. Polynomials, you can have infinite degree polynomial, it may go to infinite degree. Even if you take finite degree, if you take it as a function, you might have to deal with that as an infinite dimensional polynomial because it becomes a function. Sequence, there's infinite entries are there, right? Anyway, these functions are infinite dimensional vector spaces. Okay, for linear algebra, many at times our restriction is in the finite dimensional vector space, in a Euclidean space we will be. Okay, so you have to deal with vectors in finite or sequence in infinite case, or you have to deal with matrices. You can images and other things can be thought as matrices, etc. and then your discrete signals, sequence in terms of sequences you can interpret, and continuous functions like this. If you say a set of all continuous functions periodic, Fourier basis is defined for that, right? Sines and cosines are complex exponentials in the general sense. Okay. So any question? So the thing is, you have to deal with all these things for your signal processing or image processing in the general, very elementary linear algebra, as well as function spaces will come. That's why I say our signals and systems becomes a function space. Function space. So that is introduced at the third semester itself. Without knowing the finite dimensional spaces.
They are studying function analysis and they are studying.
Okay, any question? Okay, if there are no questions, I'll stop here. We have a tea break now, half an hour. We'll come back at 11 o'clock. Professor Raj will continue in 11 o'clock. Thank you.
Multiplication of vector is not possible. But we have vector dot product which leads to scalar.
Okay, nice question. There are only that exception is there, but the dot product becomes a scalar. It is not a vector. Even though there is entry wise, you do like this. Okay. Finally, suppose x1 and x2. x1 is in R3. x2 is also in R3 because it is there. So x1 dot x2. This is a scalar. It is not a vector. In that sense, it is not closed. You don't get the element here, right? Something else you get. That's a scalar. That is something else. So this is not closed in that sense. I mean, the one interpretation for that. That is a scalar.
Dot product or outer product?
So even in the matrix case, element-wise product is there. Matrix multiplication is a different thing is there. Okay? I mean, they are defined and their consequences as a use I am saying. Something else. But it is not an entry. Not an element of the set again. If in this, at least in the dot product case, even if you add element-wise matrices, you get another matrix. That's all. But you have to again see the properties of that one to make it a structure. Otherwise it is taken as a matrix-wise multiplication and for your some purposes like.
Sometimes we take complex numbers to represent vectors or phasors.
Oh.
Then there's a bit of a mix-up in notation that we can multiply and add complex numbers and still visualize them as vectors. So that multiplication is different. Still gives you a complex quantity, but that's not the vector that we are talking about.
You mean to say cross product and other things? Yeah, it's there. Structure-wise per se, complex is R2. As per
But there is a J.
J is there, but you denote as real part and imaginary part. Each complex, C is nothing but R2 like as far as linear algebraic structure is concerned. That's why if this is 10 by 10 matrix, it is a 100 vector it is. So it is called isomorphism. So in that sense, I just make one line comment. All RK, finite dimensional spaces are equivalent, like they are isomorphic. They have the same structure, the same idea you can use for this thing. Isomorphic means what? Iso means same, morphic means structure, right? Same structure they have. Like that, as you said, polynomial case. Suppose if I have only this is an R3 element where you have A0, A1 and A2. R3.
So we have to distinguish between the dimension of the coefficients in that polynomial and the dimension of that variable x. The power.
Here x is just an indeterminate, it's called, because it's a placeholder or something like it. Just Okay, this has one basis, it could be a constant, this is having some linear variation, this has some quadratic variation in terms of. Okay, so I'll stop here. Thank you.
Good morning. It's nice for me also to sit on your side and become a student, but first bench. I've always been sitting at the front, that's become a habit. So it's nice to listen to our colleagues here giving lectures on related topics and to see how things are interpreted and presented with different perspectives, different methodologies and background. A few observations I made in these lectures. Dr. Raghavendra was talking about a point in a certain space or an element of a certain space. So when you have an m by n image, one point in that m by n space represents an image. All those coefficients of pixels are defined. So one point. In the Huff domain, one point represents a circle, but in terms of the parameters that define the circle, the center, x0, y0, and radius c. So depending upon the formulation of the space, the parametric space or some space of variables, then a point in that space could represent many things. We saw in Dr. Shyamlal's lectures that the convolutional neural network can learn the coefficients and perform convolution. The coefficients could be specified by the user or could be learned by the network in response to samples provided as input and some training output. But my view has been the classical approach before ANN, CNN, and so on from the 1970s, which is when I learned these topics, signal processing, image processing, so on, pattern recognition, through my courses at IISc Bangalore. At that time, we didn't have these topics established well enough to be studied in this manner. So I could say that I prefer to specify my own convolutional matrix. I want to design my own method. I need to know what operations are being performed. And not everything is convolution. For example, the last topic I presented at the end, we needed to detect the breast boundary and find those contours and get the sort of difference between the expected contours and the angle of the oriented pattern determined using Gabor filters. Perhaps some of the Gabor filters can be given as convolution matrices, although large, and a number of them, a bank. That can also be put into CNN and DL and so on. But then there are some other things that may be harder to put into such a network. I would see that as more as an implementation. And you could implement the same procedure using different formats of your program, different languages, different ways of expressing matrices and operations, vectors, signals, and images, and so on. One could say that I prefer to have my input and specify what I want as output. My children used to make fun of me that a buffet, I always criticize buffets, that I don't understand buffets. They say, I understand, but in a buffet, I can't specify what I want. Somebody else has determined what should be laid out. I've been here in Udupi for 10 days. I still haven't had my kai holige, coconut paratha, if you want to call it so. Nobody has offered me, and I keep asking, and things have changed. We were here 10 years ago. We asked for holige. No restaurant offers that. They only have, everybody has gobi Manchurian and noodles and so So they have learned the way I want to connect it to what we are talking about here is the neural network of the restaurants and hotelier business people here. They have learned what from the public, general public, all the input received, and the majority of them want ice cream and gulab jamun and gobi Manchurian and something else. I want something else, and it's hard to specify that because the network has already decided something. And the same with a thali meal. I don't like the thali meal because I don't know what is coming there. I want to specify, I want this, this, this. So the classic approach would specify and provide the user more control on what I want. Whereas some of these other approaches may not give me what I want. There was one more observation. What was that? I forget that now. Okay, maybe it'll come to my mind later on. So let's move on to this today's topic of application. By the way, I have added 5 more PDF files to the folder, and Dr. Raghavendra has already put that on your folder. Please download. There is one called CAD Intro, Introduction to Computer-Aided Diagnosis. I will not go through that because parts of those have already been covered or will be covered. The others are available. This is also available. So today we will talk about digital image processing for ophthalmology. And I've had 2 students, Faraz Alomi, who did his MSc and PhD with me, and Iris Ju, who has done her MSc with me, in collaboration with Dr. Anna Els, who is a pediatric ophthalmologist and retinal specialist at the Children's Hospital in Calgary. I mentioned 3 of my students have done MSc and PhD with me, MSc by research, by thesis. What I have always told my students who have done an MSc is go somewhere else, or at least go to a different professor in the same department. I tell them clearly, if you stay with me, you will not learn anything new. I'll simply tell you do this and do that, and you will do it. So I would suggest the same to others. To gain good experience, it is nice to have degrees from multiple universities or institutes. But I also tell them, if you do your MSc and continue to do PhD with me, very likely you will get your PhD much faster than doing a PhD with somebody else, because you have to start learning again. So a few of them took that second piece of advice. Anyway, so what is this? First, why do you want to image the retina? The retina is the detector at the back of our eye, at the back of the eyeball, onto which light is projected by the lens. And retina has sensors, rods and cones. Rods are sensitive to light. Cones have 3 varieties, maybe 4, depending on which theory you look into, that are typically sensitive to bands of light in red, green, and blue. It's not just red, green, blue, but they have a certain bandwidth of sensitivity, which I'll talk about in more detail in my seminar tomorrow on color image processing. There are several diseases and conditions of the body that can affect the retina. Hypertension, diabetes are the 2 common conditions that affect the blood vessels in the retina, blood supply to the retina, and certain things change. And if not caught early enough and treated, it could lead to serious issues leading to retinal detachment and blindness. Retinal difficulties are also caused in very premature children with low birth weight. And Dr. Anna Els was interested in retinopathy of prematurity, or what is called ROP. I'll show one application to diabetic retinopathy, but our project was mainly on retinopathy of prematurity, where premature babies below a certain birth weight and lower than a certain period of gestation will have this risk of developing retinal problems. And if it is not caught early enough and treated within a few months after birth, the child could go permanently blind eventually. So there is a serious risk there. And we were interested in that project. There are some similarities in the symptoms or the signs you see in retinal images between diabetic retinopathy and ROP. But there are some that are particular. So we started working on that project. This shows me going through the standard retinal imaging procedure. In some cases, there could be dilation. In this case, there is no dilation of the pupil. You just go and sit there, and there is a flash of light applied. You get a picture, as you see at the back on that monitor. Simple procedure, non-contact, except I have to put my chin there. In the case of pediatric infants, premature infants, they are very tiny, and they are in the intensive care unit, what is called a NICU, neonatal intensive care unit, and they are in oxygen chambers. You cannot do that. So there is a camera that is used that typically requires contact. The lens has to be in contact with the eye, and I'll show you a picture that not many may like, but I'll show that picture. So imaging of the retina is fairly simple, but not so simple in the case of premature babies. Screening for diabetic retinopathy could be done using this in adults. And there are screening programs in many parts of the world and in India too. There are many institutes and companies developing software. So this field is well established, has been established over the past, let's say, 20 years. And there are commercial systems available. For ROP, also, there are companies in Bangalore. There is Narayan Nethralaya. There is a Karnataka program for ROP called KidROP. And there are many other. There is one from Stanford University in California called SunDrop. So there are many programs for ROP also. And I believe in Karnataka there is a program where social workers or hospital staff go to rural areas and look for premature premature babies being born, and then scan them, or maybe they scan all children, all babies. And there are many devices being developed, attachments to cell phones, to obtain pictures of the retina of babies, children, adults. ROP, retinopathy of prematurity, is a condition that could develop in the first 8 to 12 weeks of life. It's not clear as to what causes the problem. When a baby is born so early, I'll give you some statistics, prematurely, then the retina may not be fully developed, and after birth there could be some rapid development of blood vessels. And there is some doubt as to whether the enriched oxygen supply in the ICU may be causing some of this rapid development. So let's not look into the cause, but it exists. ROP is a leading cause of preventable childhood blindness, but childhood blindness means blindness for life. The risk factors are said to be in articles: birth weight less than about 1,250 grams, less than 1.2 kilos, and gestational age less than 28 to 32 weeks. That's a range given, but in our database, those numbers are even smaller. So the next image, I gave this seminar in Brazil once, and they told me, oh, don't show such pictures without warning me first. This is not bad, but there is some imaging procedure with the camera touching the baby's eye, and some people may not like it, so if you don't like, close your eyes. So here is a little baby, and the eye has to be, the eyelids have to be opened up, and then gel is applied to the tip of this camera. This is an old video camera. Perhaps there are better methods now, but they're still being used with what's called the RETCam. And that the lens has to touch the eye in this case. We couldn't do this. We can't even get into the NICU, the ICU for children, for neonatals. So this is done by the hospital staff. And these are some sample pictures from the database given to us by Dr. Els. She's an international specialist. She has connections in India. She goes all around the world. There are big networks of ophthalmologists working on this problem, and she's a leading expert in this area. And she has developed a database from which we got these images. These are all retinal images of premature babies. No ROP. The blood vessels look normal. I'll explain what normal and abnormal are. ROP stage 1, 2, 3. The staging is not very important. Initially, scanning is to detect initial screening is to say, is there ROP or not? And then there is a stage of ROP called plus disease, where the disease is progressing rapidly, and that is important. 1, 2, 3 may not be important. But what you see in the stage 3, where the difference is more obvious, is the angle of insertion of the temporal arcade, that is the blood vessels that go this way from the optic nerve head. That is a wide angle of insertion, or insertion, let's say. This is a narrow angle of insertion. That is an artifact of the screen. And the blood vessels get tortuous. These blood vessels are piecewise linear, or curvy linear structures, smooth. But here they are more kinky, if you want to use a loose term, but tortuous. And also the blood vessels are thicker than those. So there are 3 important developments or changes from 0 to 1 to 2 to 3. The angle of insertion of this, what's called the major temporal arcade, gets narrower. I'll show with more examples as we go along. The blood vessels get thicker. There is dilation. But dilation where is the question? All blood vessels get thinner. By the way, this is called the optic nerve head. Blood vessels come from the brain, some artery within the brain come inside here and then spread into the retina, and the veins go back that way, and along with the optic nerve, they go from here to the brain. The optic nerve carries the information, the pictorial information encoded, processed and encoded to the visual cortex in the brain. So this optic nerve head is where the blood vessels come and go, and also the optic nerve, which you cannot see. So it's a point of convergence or divergence. That's an important thing of all these vessels. So angle of insertion, thickness, all these blood vessels get thin, and then there are arterioles and capillaries, and then the venules form and the veins form, and then blood goes back. So there is a natural change in thickness. So when you say dilation, the question is, where do we measure it? That's an important question. I'll talk about that later. And then tortuosity. So these are the signs that Dr. Els described. And we set out to analyze and perform quantification of these features. So early treatment is based on the diagnosis of plus disease. It's a strange terminology, but it means ROP is going at a rapid, is worsening or developing at a fast rate. Increased vessel thickness called dilation, tortuosity, straightening of the major temporal arcade, or the angle of insertion becomes narrow. So again, compare that with this, tortuosity and dilation, and the opening, that to this. So the objectives of a study, first you have to detect the blood vessels. To do any of this, you have to detect what is called the vascular architecture, and then analyze that. So detection of the MTA and all blood vessels, and measurement of the thickness, in particular the major temporal arcade. We said we won't measure the thickness of all vessels all over the image, it's useless. They all get thin at the end, so why bother? So they specify a range as to where you want to measure the thickness of only the MTA. MTA is the major temporal arcade. Quantification of the openness of the MTA via parabolic modeling and measurement of the temporal arcade angle. The temporal arcade angle was defined in a different study by researchers in London, England. Quantification of vascular tortuosity and CAD of ROP. That was our project. Before this, you can add detection of all blood vessels. Dr. Els has been working for a number of years, decades perhaps, on developing this database telemedicine for ROP in Calgary that is called Tropic. Calgary is not in the tropics. I don't know if she meant that as a joke, but Calgary is in the, not Arctic either, but in between. Cold, not tropic certainly, not tropical. Images were captured using what is called a wide field, 130-degree field of view, REDCam 130, poor resolution. So this is what we got. Nowadays, I'm sure you can get better images, but the coupling is important. Yeah, you can take pictures with your cell phone, and there are some coupling cones or some kind of a device attachment, so you can focus on just the retina and not let light come from elsewhere. I don't know of the quality of the images that you can acquire with premature babies using the cell phone attachments. But it's being done in Karnataka in screening programs. The spatial resolution is not bad, but 30 micrometers per pixel. We only got 19 images. No signs of plus disease, we got 91 images. Well, this is what I wanted to say earlier in the context of these convolutional neural networks and deep learning and the restaurant and all that I told you. Certain things are trained by a large population. Like the restaurants want to cater to the general public, not to my specific taste. They won't make this coconut holge just for me. I'm sure they know how to do it, but they won't make it because they can't sell and make money. So when you take a specialized database like this, or when you want to address, let me turn back, when you want to address a very specialized condition such as ROP, you will not get 1 million cases. You can't train a deep learning system with 19 ROP images. You can get 1 million normal images of adults. You can get maybe 10 million or 100 million around the world. But they're all normal. How many of them are ROP of premature babies? The same with architectural distortion. You can get 1 million mammograms. In fact, from the screening program, when I asked them to digitize, scan mammograms, they brought 1,000 normal mammograms. I said, no, I don't want 1,000 normal mammograms. It'll take us a year to scan and handle them. Get me a certain proportion with abnormal conditions. As I mentioned earlier, in a screening program for breast cancer, only 0.5%, 1 in 200 women will be found to have breast cancer. Maybe 10% will have some other breast abnormalities. And of those 1 in 200, how many will have architectural distortion? Very few. So you will not get 1 million cases of architectural distortion to train. You train with 1 million normal mammograms, how can it find that one needle in the haystack that has architectural distortion? The same here. We only got 19 with ROP. And all of these are from premature babies from the Alberta Children's Hospital. We had 91 with no signs of plus disease, but various stages of ROP, and normal too. So the statistics, birth weight, 800 grams. Gestational age in weeks, that is, when was the image taken after birth? About 26 weeks or 25 for the 2 data sets. Wait a minute, sorry. Gestational age is the period of the pregnancy in weeks, only 26 or 25 weeks. The chronological age is number of days after birth when the image was taken, about 2 months. So the gestational age or the period of pregnancy is also very low compared to the normal, which is between 36 and maybe 40. 40 is considered normal, I think. But 36 to 40 is the normal range, and these babies are very premature. And the birth weight is only 800 grams on the average. So these numbers are much lower than what the textbooks quote as the risk factor. So we also use the DRIVE database, a public database for which with which many papers have published their results of vessel detection, blood vessel detection. These images are also not of very high quality. These are from the 1990s, 500 by 584 by 565 pixels or 20 micrometers per pixel. Now this number looks good, but the overall size is small. Dr. Els marked some of these features. She traced the temporal arcade. She drew the boundary of the optic nerve head and so on. Marked the tortuous vessels for training. So here are examples from the DRIVE database. This is not pediatric. So this is the optic nerve head, the fovea that is within the macula. The dark area is the macula. And there are not many blood vessels in the macula. That's where there is a high concentration of the rods. That is where we get high visual acuity or sensitivity. So because of the higher density of the rods that are the sensors, there are not many blood vessels there. As you come to the optic nerve head, there are no sensors there. So this is the blind spot where there is no detection. The superior part of the temporal arcade and the inferior, in this case, the temporal arcade is the other way. Okay? So if you were to look at a certain part of it close to the optic nerve head, it is approximately a parabola. As it goes out, there is some convergence back down, and the blood vessels go that way. So for parabolic modeling, we consider only a small portion here with reference to the optic nerve head and the fovea. There are many algorithms in the literature to detect the optic nerve head and the fovea. The fovea is hard to detect. In the case of ROP with premature babies, the fovea and the macula are not seen at all. So it's not possible to detect the fovea. The pre-processing steps, we use, this is a color image. We use the luminance component from the YUV representation. I'll talk about the representation of color images later on tomorrow. But you take that Y and that is given as this combination of RGB. That's a standard definition. So it converts the color image to just this intensity image. Or this is the intensity component of the color image, with the other two components being the chrominance components or color components. To get the effective region, there is this black area, there is this boundary which causes serious issues in edge detection on blood vessel detection, because this is a very strong edge. So to process this non-square image, that is, we are interested only in the circular part, and all the image processing algorithms, Fourier transform, they're all based on square arrays. We had to do something. So we wanted to get the effective area. What is the part of the image where you have the retinal image and the rest is background? So we thresholded by using 0.1 as the threshold on the Y channel. But then we wanted to fill this background, the rest of the black area, with some continuity in grayscale. So we applied morphological erosion with the disk structuring element of radius 10 pixels and replaced the pixels at the outer edge of the effective region by the mean over a 21 by 21 neighborhood. This is to remove any artifacts in the detection of the boundary, and then keep padding that with the average and keep going until you reach the boundary. So instead of this sharp boundary now, we have this relatively smoothened image. So we don't get artifacts related to those edges. Otherwise, those will get detected as blood vessels. So merge the effective region with the outer edge pixels to form this extended effective region, and repeat it 50 times and keep extending it by a ribbon of width 50 pixels. Apply a median filter and get a reference intensity as the maximum of in the result of the whole image. So we wanted some reference intensity as to what is the average or reference intensity or brightness of this image. Gabor filters you have seen, so I won't repeat. We are detecting oriented structures such as these blood vessels. And this you have seen before, and this you have seen. So here we have the inverted Y channel. To use the cosine function in the Gabor filter like this, it is detecting bright objects. It won't detect dark objects. If you want dark, you use the sine function to get a dark line in the middle and white side lobes. Anyway, the side lobes will be dark and white, or dark and bright. So we inverted the Y channel and got this image where the blood vessels are now brighter. The Fourier transform, it's a little hard to see. If you zoom in, you will see some oriented components. So you see that, I suppose. this concentration of energy corresponds to blood vessels perpendicular to that. So these lines contribute to that. So by using a Gabor filter at 45 degrees, we extract these components. That is there and this is here. Gabor filters, we used a bank of filters. This is one filter. By using a bank of 180 real Gabor filters, real meaning cosine only for modulation of the Gaussian, minus 90 to plus 90 degrees, that is minus 90 is downward and plus 90 like the y-axis. Elongation L, thickness tau, 7 pixels. These parameters were varied depending upon the application as to what you want to detect. The Gabor magnitude response at each pixel is the maximum of the filter response over all angles at every pixel for a given pixel. And the vessel orientation is given by the Gabor angle phi p, for which you get the maximum response at that pixel location. So that is the orientation field. So for this image, all the blood vessels have been detected by taking the Gabor magnitude maximum over 180 Gabor filters. And for each of those filters, each of these pixels, you take the angle of that filter that gave the maximum response. And for this little window, you see the vessel like that, which is here. The angles agree with the orientation of the blood vessel. Those lines are drawn only for every 10th pixel because you have to draw that line. So in between also, we will get, for every pixel, we get an angle. In the background, the angle is irrelevant. So we don't have to really show those angles. We could say if the Gabor magnitude is less than some threshold, don't show the angle. But here we are showing all angles. So like this, we get the angle for every pixel in the image. And then you have to threshold this. So we tried various thresholding techniques. I won't go through all of that. Depending upon which thresholding method you use, you get some result. And in the drive database, there is a reference given, binary pixels of the vessel map that you can compare your output with. And there are many papers where that has been used. And Chowdhury, this is Subhashish Chowdhury, who did his MSc with me, then PhD at the University of San Diego. He did this work, and it's a highly cited paper. I don't know how many thousand, many thousand citations for his paper, using matched filters. Using Gaussian filters of different scale, matched to the orientation, rotated, and when it matches the idea there is if you take a blood vessel and if you take a section, it will have like a Gaussian distribution of the intensity in the projected image. So they used match filters, they got 0.91, but then there are many other papers after that. Once you show that, then there'll be a whole string of other papers telling, oh, you got 9.1, I'll get 9.9. So we didn't get 9.9, we got 9.5 and 9.6. And we were talking about Gabor filters, and I had met Soares in Brazil. He did a work on multi-scale Gabor filters and got 9.6. And I'm sure there are others with deep learning who can get not more than 1, but 999 something. These are area under the ROC curve with 20 test images from the drive data set. So vessel detection is well established. There are hundreds of papers perhaps on this. To detect the ONH, Iris Jew, she did her MSc on this project, and she started with the Sobel operators to get the edge map, and you get the two gradients gx and gy, and take the magnitude. You have seen all this threshold to get an edge map, and then apply the Huff transform. I have shown the Huff transforms for circles. X minus a plus y minus b square equal to c square. And xy equal to ab is a center, and c is the radius, and in the Huff space, a single point ABC represents a circle. The accumulator is defined as A of ABC. So the procedure is obtain a binary edge map of the image, set values for A and B, some range. We know the optic nerve head is this big. We know the dimensions, the range of the dimensions for pediatric cases and adults. So we don't want a circle that big or this small. So set a range for the half space parameters A and B. A and B must be inside the scope of the image, but also we could say it has to be on a certain side, but it can't be always macula centered. Sometimes some images are ONH centered. Most of them are macula centered or fovea centered. So it depends on the imaging format. So it may be difficult to set limits on A and B. So you can say we'll use the entire space of XY. Update the accumulator corresponding to, for every pixel corresponding to ABC. Update the values for A and B in the range and go to the next step. And we put these limits, average diameter of the optic disc. It's also called optic disc. There is a minor difference between optic disc and optic nerve head, but let's ignore that. The average diameter is 1.5 millimeter for the drive data set of adult images. The radius of a circular approximation to the optic disc was put in the range of 600 to 1000 micrometers. And spatial resolution 20 micrometers, so the range for the radius was 31 to 50. So a range of, we need 20 slices. But the parameters of the 20 slices go from 600 to 1000 micrometers. This is the size of the image, 584 by 565. So here is the half space for this edge map of the entire image. We could have done something more, but at that time, Iris did this, and the circles intersect there. There's a peak there in C equal to 37, and others don't have such a peak for other values of C. These are slices of the half space. But the global maximum may not be the circle you want, so you search for a number of maxima. Select the top 30 peaks in the 3D half space that correspond to 30 potential circles indicated by the half transform. Use the property of brightness. Inside the ONH, we expect the brightness to be high normally. You will see it doesn't always work. We expect the ONH to be circular, not always. But anyway, it has to be bright typically. So we said the threshold of 90% of the reference intensity computed earlier from the entire image. So we expect this to be brighter than that. Some average value within that circle must be brighter. So this is the result. Edge map and the circle detected and the center. So this was good, but in this case, maybe. You see, there is sort of a circle here and another circle here. It's not a perfect circle. Giving excuses as to why it didn't work. But real images pose such issues. And here it is very dark, hard to see. The edge map is not showing a circle. And the best circle was that. And here there are some exudates, these yellow bright spots. So that met the condition of the intensity. And the best circle was that which is totally out. In this case, there is some region here that is so bright. That was found to be a circle somehow, but that's not correct. So we said, well, that is an interesting initial step, but not perfect. And there are other criteria we could look into. And the other one being all blood vessels converge or diverge from this area. Blood vessels, they don't intersect as such like the spicules in architectural distortion, but they emerge from within the optic nerve head and then go back there. So regardless of the intensity of the optic nerve head, this property is fundamental. Blood vessels have to come out from there and go back there. The optic nerve is also there, but you can't see that. So this convergence property is more important, and it has to be there. Not a circle, not the bright region, the previous assumptions. So we said we will use the orientation field like we did before. Now one could criticize, and one does criticize like this. Suppose I make this presentation somewhere, somebody will ask me, why did you use Gabor filters? Well, oriented structures and fine. Why did you use this orientation field and phase portrait analysis? Well, they do converge. So we have to explain as to why we chose these methods. But the common criticism is if the only tool you have is a hammer, every problem looks like a nail and you just bang on it, and whatever it is, you only have one tool, the hammer, and try to bash everything with that. That's not true in this case. We have some reasoning as to why we want to apply, and you will see that it works, this approach. So extract the orientation field using Gabor filters, filter and downsample to remove artifacts and noise, analyze the orientation field using phase portrait, post-process the phase portraits, detect sites of not architectural distortion now, but convergence of blood vessels, select a point of convergence. Now again, there are confounding factors. So phase portraits you have seen just yesterday, was it, or day before? So here is this analysis window. The image is some 500 by 500 something, and the window is 40 by 40 pixels. So within that, you take these angles, and you want to find A and B parameters. A is symmetric, so there are only 3 values. B has 2 values, so 5 values in the model to be, so that is symmetric. So what is that? So those parameters need to be estimated from these angles so that the phase portrait model will generate a flow field or orientation field comparable to this. That is through nonlinear least squares and simulated annealing, for which Fabio had developed some programs. So the project continued in that direction. You cast a vote at this point, fixed point of that phase portrait minus A inverse B. That gives you the location. The window could be there, but it says my patterns here converge there. So that is where you increment in the node map. The window could be here. It says the fixed point is somewhere there. Then you say, no, I'll throw it out. So the saddle is that where we don't have anything in this area. The node has a number of votes cast in that area. Now you post-process that, accumulate and do some filtering and thresholding. You can find the point of convergence or divergence of the blood vessels. So this is the point that was marked by the algorithm. Dr. Els drew the boundary of the optic nerve head in some of these test cases. She marked where she marked what would be called a reference point in the optic nerve head. Is that the point of convergence of the vessels, or is that sort of the geometric center? We don't know. She gave us one point, and our method gives a point. So we computed the mean distance to closest point between the contour drawn by the ophthalmologist and the circle detected. And in this case, just a point, the Euclidean distance between the reference point given by the ophthalmologist and that detected by the method, and verified the results. So for the 40 images in the drive database, the first peak in the node map, if that was used as the optic nerve head point, one point is detected, not the contour. The distance was 1.6 mean with standard deviation 2.4 in pixels. Where is the millimeter? Sorry, that is millimeter and this is pixel. In parentheses, pixels. 1.6 millimeters and 2.4 standard deviation in millimeters. If you apply the condition of intensity that around that point, if you take an average in a neighborhood, that it should be brighter than the reference, then a better point was selected, with the error being 0.46 millimeter. Now we had a question as to what was the point that was marked by the ophthalmologist. Was it the center of the optic nerve head, geometric center, as I mentioned? And we did say that this method will detect the point of convergence or divergence of all the blood vessels, but then it's not one point. You see, all of these, there is some common area there. So depending upon where the ophthalmologist marks the point, there could be some difference between what is detected by this method and what is marked as the reference. Anyway, we got a point in the optic nerve head. We just need one reference point, and that's adequate for subsequent analysis. To measure vascular thickness, we said we will use the MTA, the major temporal arcade. The retinal vascular changes can be indicative of diabetic retinopathy, ROP, and hypertension, as I mentioned, and in all these cases there is an increase in the width or thickness of the MTA. Some call it diameter. Small changes are hard to detect by the naked eye, especially in the case of ROP. Those vessels are so small, so how do you measure or estimate the thickness and compare? It's difficult. So the processing steps were take the Gabor magnitude response, normalize and divide into the upper or superior and lower inferior parts using the center of the ONH. The center or the reference of the ONH was detected using this method that I showed. 1 point is enough. All we want is the upper part and lower part. So we can model them separately. They were enhanced using gamma correction, binarized and clean with morphological area open. The ONH and its boundary were removed, and branching points on the skeleton were removed. We got a skeleton after that. Each skeleton segment was labeled with a number. To track the MTA, a seed was selected automatically, labeled with the highest average Gabor magnitude in a region around the ONH. We have 1 point around the ONH, search, and from there the vessels are coming. They'll be the thickest, the vessels will be thick there, thickest over their path. So depending on the Gabor parameter you use, in this case we used a large value for the thickness, tau. So we detect only the large vessels, the small vessels are suppressed. So multi-scale filtering, you use the thicker scale. So find a pixel near the ONH that has a large response for the thick Gabor filter. And the next segment is the neighboring label with the highest average magnitude response, and keep going like that along the vessel. You are tracking the vessel from the ONH. So the vessel is marked into segments. I'll show some examples soon. Then we need to find the vessel edges. We have the skeleton, which is not necessarily the center line. The skeleton is somewhere inside the vessel, and then we have the vessel boundaries. To measure the thickness, we want to draw a perpendicular to the skeleton line at every angle. We have the angle, every pixel. We know the angle of the vessel at every pixel from the Gabor angle output. So we draw a perpendicular, and until the perpendicular crosses the vessel edges. So we need the vessel edges. So we compute what's called the mean absolute deviation of the Gabor angle response of the MTA segments to select linear segments. When the vessel is curving, it's a bit hard to measure. The angle is changing. So we break the vessel into linear parts. And for that, we analyze the angle. We use Canny's method here to obtain edge pixel candidates for every linear segment. Interpolate the vessel edges as two lines fitted to the edge pixel candidates on either side of a linear segment. We know the average angle of the skeleton, so use that angle and fit straight lines on both sides. And then you can measure the thickness. Obtain the normal line at each MTA skeleton pixel using the Gabor angle response. Obtain points of intersection between the normal line and the two edge lines, and MTA width is that distance between the 2 points of intersection. So this is all done automatically in the program rather. So here is an example of a case with no plus disease. This is a premature infant. The Y channel image, blood vessels detected, Gabor magnitude response. So this is only the upper part of the temporal arcade. The optic nerve head is somewhere here and the lower part is here. We analyze the two parts separately, get the skeleton, remove all these pieces, and finally we get this and break it into parts that are almost linear. This is the Canny edge output. So on either side of this line there will be two edge lines. So for each point here, draw a perpendicular until it crosses those two edge lines. These are the perpendicular lines shown graphically. And at points where the curvature changes or the line segment orientation changes, there is a new line, a segment there, a segment here, from here to there is another, that is another segment. Or if there are blood vessels intersecting, you cannot measure thickness, so throw those points out. And for the inferior part, all done automatically, and if we don't like the word automatic, computationally. So we take the average of these and we go only up to a certain distance from the optic nerve head reference point, which I believe is half the way to the macula. We don't have the macula, so we estimate some distance and say we only measure the thickness in this portion of the image from here to there. This distance is known through statistics. So we cut the image for that distance from the optic nerve head. Because after this, the curvature changes, the thickness changes. Where do you measure thickness? And if I measure thickness all over, then the average is meaningless. So that's the measurement at 111 plus minus 18 micrometers. For this case, without plus disease, and with plus disease, 125. So thicker, as you can compare that and that visually, same scale, same process. Okay, that is dilation. So we're not measuring an average thickness of an entire vessel, and we're taking multiple measurements of the actual thickness at multiple points in a limited region. So we can get not only an average thickness, but also some standard deviation if you are interested in that. So these are the points where the thickness was measured. A few tens to a few hundred points. So for no plus, 91 cases, the mean was 110 micrometers. Minimum, maximum there, let's not worry about that. Plus disease, 125. And that was significant to P equal to 0.002, highly significant difference. But the diagnostic accuracy in terms of ROC was 0.76. So sometimes the statistical p-value we found was not very meaningful. The p-value is so low, it says it is statistically highly or very highly significant, 3 stars, 4 stars, and all that. In terms of ROC, it doesn't show that. There are two very different ways of measuring the value of your parameter. But still, we quoted those, computed them. In the diagnostic situation, area under the ROC curve is perhaps more important because you want to catch not only plus disease, but also all the no plus diseases must be marked as negative. That is, you must have high sensitivity and also high specificity. And the ROC area tells you that. We tried to compare various stages of ROP, stage 0, 1, 2, and did the comparison between the various possibilities of this S0, 1, 2 to S1, S2, S3. Only comparing with S3 turned out to be statistically significant. The others were not significant. In any case, Dr. L said that staging is not important in initial screening. Our next is modeling. We said we are interested in that opening of that arcade, which we said is a parabola. Is it that big or is it this narrow? Narrowing is not good. Narrowing means there is some scar tissue that is pulling on the vessels, and the vessels are going like that. So we use the Gabor magnitude response with a large value of thickness tau equal to 16 to get the MTA, because that's what we are modeling. The rest of the blood vessels, we don't care. Binarized, skeletonized, the skeleton image cleaned using morphological area open. So this is what we get. And here again we put that limit on where we want to apply that model, only to that portion with reference to the optic nerve head. Now this is an image from the DRIVE database. Vessel band, Gabor magnitude response, skeleton. Cleaned skeleton shown with thicker lines just for display. It doesn't matter we thought we should remove all these little pieces, but when you use the Hopf transform, it doesn't matter. These will cause a little bit of noise in the Hopf space, but there is a big parabola clearly there, and you could fit a little parabola there, but it is way somewhere else. We want all the parabolas to pass through the optic nerve head. Otherwise, we reject them. So some of these artifacts are not important. They can stay. If you want, you can keep cleaning further. So the equation for the parabola y minus y naught square is 4ax minus x naught. A is the openness parameter, x naught, y naught is the vertex. So again, we have a 3D Hopf parameter space. So one point in the Hopf space with these parameters will define a parabola in the image domain. So that we have seen. The MTA follows a parabolic path up to the macula only. And after that, it sort of bends downward or inward. Given that the macula is about 2 times ONH width, temporal to the ONH, that is in this direction, this is the temporal area of the brain, or these are also called the temples, so temporal, I suppose, refers to that. 2 times the ONH width, and that has been, statistics of the ONH width are given in the literature. And with the prior knowledge of the ONH1 reference point, we restrict the horizontal size of the Hopf space. So the size of each plane now is the full height of the image, 580 pixels, but only 170 pixels in width for the drive images. For the tropic images, we used other parameters. So anatomical restrictions on the Hopf space, the location of the vertex of the desired parabola in the Hopf space is restricted to be within 0.25 times ONH width of the ONH center or ONH reference point detected previously. So we are saying, give me a parabola that is there with its vertex, not some other parabola. The value of A also has limits. That is the openness of this MTA. It can't go straight like that. It cannot be like this. So there is a certain range. So we said the range is 35 to 120 for the drive images. That is just a parameter. The number of planes in the 3D Hopf space is 86 for this range. So here also we tried some of the concepts I mentioned earlier. If you update the Hopf space with unity for every skeleton pixel that has remained, you get this very busy Hopf space. One slice. This is only one slice of the 3D Hopf space. Hopf space, if you take this and say, I want only the points in this region with the vertex and horizontal size restrictions, you are limiting only to this portion, and even a circle, the distance of the vertex must be less than some distance I specified with reference to the point in the ONH. We are searching only this much in the plane, Hopf space plane, and that in 3D. If you update the Hopf space with the Gabor magnitude, that is, the accumulator cells are not incremented with unity, but with the Gabor magnitude response at that pixel, then higher Gabor response means a thick vessel. That's what we want. And there is a vessel and not some other background detail. So all of these in this section will be reduced to just that, and you put the distance condition, it's only that much. So our search in the Hopf space is limited to this little circle for every plane. And I said there are a certain number of those planes. So then you get to find the best fit, best parabola out of that. And for this image, we got that parabola. We have drawn the parabola with no limits on space, but the fit was done only so much, using this much of the information, as I showed earlier. Later on, we felt we shouldn't have drawn the parabola like that. Anyway, for illustration, that's the parabola that was detected. For the superior part, it is matching the MTA well, but the inferior part, the vessel is going here, it is not fitting. So sometimes there could be a little bit of rotation of the image. That is, the axis of the image, what is called the retinal raphe, joining the optic nerve head to the macula, to the fovea rather, It is like that. So the image is tilted a bit. So then we said we will split the MTA into superior and inferior parts and fit a parabola to each one and take only half the parabola. So we got that, which is having a good fit similar to that. Here we're getting a better fit. The vessel is there up to here. So we get two parameters of the two parabolas. So we call this dual parabolic fitting. So this is the contour of the MTA drawn by Dr. Els. And this is a single parabola, the red one, if you can see that. These cyan lines are the MDCP, not MDCP, DCP, distance to the closest point. So from here, find the closest point and take all those distances and average them. That gives you MDCP. And that was 11.5, but with the dual model, it's only 3.1 pixels. So there are two parabolas here. Can you see the red line? No. Perhaps you can see the red line better. That's a parabola. The green line is the reference contour drawn by the ophthalmologist, and that's the reference point in the optic nerve head with two different parabolas. The vertices of the two must be in a certain distance, within a certain distance from the reference point. They don't touch in this case. It doesn't matter. So two half parabolas better than one parabola. There is this temporal arcade angle that was defined by a group in London. We went and met them. We were hoping to collaborate, but not much happened after that. It is measured using a graphical user interface. The user has to mark some points. The user is prompted to mark the center of the ONH. A circle with a given radius is drawn on the image, and the user is asked to mark the points of intersection of the circle with the superior and inferior parts of the MTA or venules. They are veins, so venules. The TA is measured at the angle between the three manually marked points. But the method depends upon how well these are marked. These points are marked manually, and what is the size of that circle, how big that circle should be. So TAA, if you take the radius to be 60 pixels, you get 156 degrees here. If you take it to be 120 degrees, then you get 120 pixels, you get 140 degrees. That is the angle. This is the ONH marked, and those are the intersection points with the MTA. 3 points have to be marked by the user. The AMTA, according to our parabolic modeling, the value was 78. If you did the half parabola or dual parabolic modeling, 72 and 78. This is no plus disease, a premature infant here. With plus disease, it is much narrower, as you can see. Both single and dual parabolic modeling gave the same answer, 10. So 10 compared to 72 is much smaller. And the angle, it was 156, 140, now it is 87, 79. So that is narrowing of the major temporal arcade. So we did some statistical analysis of significance and confidence interval and all that. 19 cases with plus disease compared with 19 randomly selected no plus cases. We had 91 cases. So the data set is not balanced. So we said we will choose the same number. We have 19 with plus disease, so we chose 19 from the other set, no plus, but we can repeat it many times. Keep sampling. What is called bootstrapping. They could be, it's up to you to decide if you want repetition or not, a replacement or not. If you want to do it many times, you have to replace, sampling with replacement. The TAA turned out to be quite good actually, 0.74 mean area under the ROC curve, and the AMTA also STA, superior arcade, they both gave 0.7. The inferior one did not give a good value for area under the ROC curve. So the combined model was adequate. It gave a result that is comparable with the TAA. Now, it is possible to compare these and ask the question Dr. Raghavendra said, is that statistically significant? Can I claim that my method is better than that? There are methods to compute p-values between ROC curves and between FROC curves. We have done that in other studies. So there is some statistical significance that Faraz did, and the details are in his papers. So I'll not go into that. But anyway, they're all in a comparable range of around 0.7 plus minus 0.02 or something like that. We applied this to a data set of proliferative diabetic retinopathy, or PDR, that we got from the STARE data set. STARE is another data set that has cases of this PDR where you see this difference in the insertion angle. But these are extreme cases in the sense it's very close to retinal detachment, not early stage of diabetic retinopathy, but late stage. So modeling and analysis here is not really very useful in a screening situation. Anyway, we had the data set, so we wanted to check if this is useful, and it turned out to be fairly useful in diabetic retinopathy, but for proliferative diabetic retinopathy, late stages, where the distinction can be seen here, normal and PDR. And we got better AZ values. Arcade angle 0.8, the MTA single model 0.87. Here the inferior angle gave better result, 8.2. Area under the ROC curve and some other statistics. So coming back to the ROP situation, the third observation, clinically observed and what we wanted to quantify, was tortuosity. So we studied the literature and found that there wasn't much done on tortuosity, or the measures that were defined were averaged over the entire image in some way, or they were measuring some vectors and angles of some vectors, and they were not really quantifying tortuosity as such. So we said we need something very specific to tortuosity. And a vessel is not tortuous right through. It could be tortuous, then the straight segment, another part that is tortuous. So that is one thing. The other is, where is tortuosity present in the image? Which quadrant of the image, at what distance from the ONH? So you can break the image into quadrants, or you can take radial distance and say this is around the optic nerve head and this is outside far away from the optic nerve head, and so on. So these are important considerations in clinical practice, and none of them addressed some of the questions I'll describe now that I have already mentioned, but I'll describe some more. The tortuosity of vessels increases in the presence of plus disease and also diabetic retinopathy. That's fine. It does not have a formal definition as to what is mathematically tortuous. And quantitative analysis should be clinically relevant, not just give some number. If the number doesn't make sense to the ophthalmologist, it's not useful. It may make sense to us as engineers, some fantastic number, but if it cannot be interpreted in the context of the image. I mentioned some of the gray level co-occurrence-based statistics are very difficult to interpret. I don't know what those later H11, 12, 13, 14, I don't know what they mean. There's some statistical something. And nobody has described. I went back, searched and searched, even in the original paper. There's no interpretation as to what they represent in the image. The first few, entropy, variance, fine, we all understand. So we need to derive measures that make sense to the user, the ophthalmologist in this case. The published tortuosity measures do not consider the orientation of vessels or use skeleton pixels. So they don't even consider the angle along each vessel because most methods don't give you that information except Gabor filters. So what are the processing steps? We get the Gabor magnitude response, binarized clean with area open, skeletonized, and small spurs, small pieces of up to 5 pixel length are removed. Branching points are removed. Each skeleton image segment is labeled with a number. Now the vessels are in pieces. At branching points, you cannot measure thickness, you cannot measure anything. It's a big area there that is common to multiple, or even intersection points, branching or intersection points. Linear parts. The vessels are curvilinear, and then there could be some tortuous part, or it could be tortuous here and then straight. The linear part should be thrown away. No point in making any measurement on them. So linear parts are identified using the mean absolute deviation, what is called the MAD measure. MAD is mean absolute deviation of the Gabor angle response. So here is an illustration of that measure. So here is a vessel segment from one of the images, and the Gabor angle at every pixel along the blood vessel, not in XY, but distance along, passing along this contour. These are pixels along the contour. The Gabor angle is there's small variation, and then it changes. So there is a portion where there is not much variation in the angle, so it is straight. So no point in measuring tortuosity there. So get this normalized MAD measure, and the linear samples are these. We take out a few points that are connecting these parts. There is some variation here, not much variation here. So these pieces are linear, these two pieces. So take them away and we get these segments. This is tortuous. Is this tortuous? Not really, but we are allowing some variation. We could be stricter in defining what is linear or nearly linear and perhaps remove even that. So one of the very basic definitions that we started with was this. We said at every pixel on that contour along the skeleton that is within the vessel, not right in the middle, it's not the center line, but in the middle, within the vessel, we said we are tracking that and we know the Gabor angle at every pixel. So all you do is compare the angle at one pixel along the vessel minus the previous angle at the previous pixel and at the next pixel along the contour, not a 3 by 3 or anything. And if the difference is small, sign is small. If it is 0, sign is 0. And average forward and a backward. This is backward and that's a forward difference. Two differences average the sign values. Take the magnitude, the difference could be negative, so half of that, and average that over all the pixels belonging to that vessel segment. Not the whole vessel, but that piece. And this is normalized by definition to 0 to 1. So we always check the methods or ideas with some test images. A straight line should be 0. A little curve, more and more curvature, very tortuous, that number is increasing. Tortuosity is increasing with frequency and length of that. See here, there is tortuosity, but it's reducing there. So some confirmation of the idea of what we call proof of concept. Now, how do we relate this to the clinical notions? A clinician doesn't want to get this number, AVT is some number 0 to 1. It doesn't make sense. We used an independent training set to obtain AVT threshold to detect tortuous vessels. So we asked Dr. Els to mark pieces of vessels that she considered to be tortuous. And we obtained the AVT value and then used that as a training set and set a threshold on AVT. Minimum tortuous vessel length was also determined using the training set. How long should a vessel be crossing this AVT, have AVT measure greater than the threshold in order to be substantial or significant. When I use the word significant, some others said, oh, you mean statistical significance? What is the p-value? I said, no, I didn't say statistical significance. I used significance as an English word. So when I say significant, sometimes I change and say substantial or meaningful. So what is the meaningful length before you say, yes, it is tortuous? And how long, what should be the total length of all these tortuous vessels in order to say that that patient has ROP? Plus disease is diagnosed if at least 5 millimeters of tortuous vessels are present in one quadrant of the image, or 2.5 millimeter present in each of two quadrants. So that was the rule that we came up with in consultation with Dr. Els. So here is an example. This is a part of the vessel being tracked. These are the Gabor angles. Now we are drawing these lines only for vessels, not for the background. Gabor magnitude response and skeleton and trimmed skeleton. These are the linear parts thrown out. These are the curved parts. And the curved parts all pass the test of threshold AVT, so they are marked as green just for display. So no tortuosity here. These are the actual vessel segments that were detected, and analyzed, and zero tortuosity, 0 millimeters of tortuous vessels. They passed some threshold for tortuosity, but other conditions were not passed. So all of this done automatically in Faraz's program. Then this is a case with plus disease, some examples of blood vessels with their angles. Gabor magnitude response, the skeleton cleaned, linear segments removed. This is the remaining part. And here you see the don't go to the next page. The tortuous parts marked in red, just for display. Now, is this tortuous? Well, it passed all the tests. We could change the parameters, but we are measuring, there is some variation in angle. The thresholds could be changed if you wish. But that is clearly tortuous. So here are two more examples. No plus disease, just those two little pieces. So that would fail the length test. Here, many of these segments are marked. And if you were to add up in this segment, you would get more than 5 millimeters total tortuous vessel length. So that is something the ophthalmologist would understand and appreciate. There are all these blood vessels. If Yanni can show, and she could look at this image, but we could simply say in this segment, in this quadrant, the fourth quadrant, there are all these blood vessels. The total is so many millimeters. Or you can give all these numbers per quadrant. There are a few more issues that I'll mention. The AVT and the diagnostic decision-making criterion were applied to 91 images without plus disease and 19 with plus disease, and we got a sensitivity that is quite high, 0.89, specificity of 0.99, and area under the ROC curve 0.98. This was unbelievable, so I told Faraz, go and do it again and again and again, checked again and again, and it worked well. Specificity like that and will usually come with sensitivity going way down to 0.7 or something like that in most other cases. So we were really happy with this result. And this was only using that measure of tortuosity. When we combined, I don't have all of that. When we combined the other MTA thickness and opening parameter and put them through feature selection, this was selected. And if we stuff all of them together and push through pattern classification, only 3, 4, 5 parameters, we got similar results, but a little lower, like 9.7 or something. But feature selection said this is the only feature that matters, and using only this, we got this result. But this is with a small data set that you should remember. There are only 19 cases of ROP and 91 cases without ROP, but of pediatric cases, premature babies. So it is a specific data set. So as I said earlier, it's hard to build a big data set of ROP cases. Perhaps it's happening in Karnataka. If you're interested, you should contact the KidRock program through Narayana Nethralaya. I tried to get in touch with them, but nothing happened. But I know Dr. Els is collaborating with them. So I don't know what went wrong, and we couldn't establish any connection. But anyway, we did this, and for us, after his PhD, he was my last PhD student. After that, we closed the lab and cleaned out everything, and he was very unhappy. He was almost crying, and I was happy. I'm retiring. He said, you're closing the lab and all of this. They're just computers. They're old computers, and nobody wants them. Anyway, he started his own company. He's in Switzerland. He has applied for some patents, and we have published all of these. He set up a company, and I was a consultant for his company, and Ben Lavoie, who is my co-author for the second edition of the book, was a research associate for this company. We developed more algorithms for ROP that I'm not at liberty to talk about because Faraz has the patent application pending for that. But anyway, these are the important criteria for ROP, and I was happy with this part as one of our last projects in the lab in Calgary. It seemed to work well, but as I said, we have to take this with, as we say, a pinch of salt and say, well, the data set is small. We applied for more grants, and as I said, granting agencies and reviewers think in a different way. Sometimes we would criticize and say they're on a different planet, they're on Mars or somewhere. They would say, okay, get 1 million cases of this and 1 million of that, and get 10 ophthalmologists and get them to draw contours 10 times. It's impossible. You can't do that. And they want the statistics. How many babies are born premature? We had that. And how many of them have ROP in Canada? Maybe per year, 10, 20. They said, oh, we don't care. How can you say you don't care? It's an important problem. We didn't get grants, so the project sort of stopped there. So many of these projects do not progress beyond a certain stage because of various other factors. Academically and in terms of research questions, they are interesting and worth examining further. If a baby goes blind for the rest of his or her life, then that's a disastrous thing. But if you say there are only 10 such babies born in Canada, Canada has a population of 40 million, half of Karnataka, I think. So they say, well, doesn't matter. But around the world, if you say, the research is not only for Canada, it's for the whole world. Sometimes research grants are competitive, so you have to find something to push you out, some limitation. Anyway. So the conclusion is what we all believe in, that image processing techniques are wonderful and they can solve all problems in the world. Engineers can solve all problems. So image processing can assist in quantitative analysis. Again, I keep emphasizing quantitative, and pattern recognition techniques can facilitate CAD. And CAD of ROP can assist in improved diagnosis, analysis of the effects of treatment, and clinical management. So not only diagnosis, in my last lecture on Friday, I'll talk about some general things, no equations, no pictures, just general chatting as to what is all this about, where do we want to go with this. But not only diagnosis, but analysis of effects of treatment, we try to do that. Dr. Els does the treatment also. There is some laser therapy and cryotherapy and so on. They do that. And then we want to check after the treatment, has the MTA angle changed or something has happened, and we got an even smaller data set. Not enough for statistical analysis. We got a few cases before and after treatment and compared, and yes, we could see change as expected, but not enough to clearly say with statistical confidence that the method works. For that, we need a bigger data set. So we got a few grants from various agencies, and Paola Casti in Rome, she did part of her master's and PhD with me in Calgary also. And Eliana Almeida from Brazil, she had come to my lab to do part of her work on lung disease classification, and April Ingram, she prepared the tropic database. So that is about this project. Any questions about this? Just a minute, yeah.
So here we used dual parabolic modeling. So I got to learn that this is not very sensitive to check in the early stages.
What do you mean by that?
We are getting this for retinopathy of premature baby, isn't it? So this method, dual parabolic modeling, will not be sensitive in the early stages.
How do you say that? What makes you say that?
I just read it somewhere right now.
You read it somewhere?
Yeah.
Okay.
I was just reading the limitations of this work, and I added that it is not able to capture individual variations, and it can overfit the data set.
Overfitting the data set depends upon the number of samples in the training set and as compared to the test set. So overfitting in pattern classification is a different issue. If the data set is small and you're making a small number of measurements, or you're making a large number of measurements, then you're overfitting to that data set. And if your test set is too small, then that matters. About whether it is sensitive to early stages of ROP, that we have not tested, because we only had we had an uneven data set. We didn't go from one stage to another to compare. We did that with thickness. One of them I showed, right? What was that? Oh, perhaps you're right. Let me go back to that. No, that we did with MTA width. Is this what you're referring to?
Yeah.
That was with MTA width, not the parabolic model, where if you compare no ROP with stage 1 ROP, these are the p-values. This is not significant. And comparing S2 with S0, second stage, with no ROP or first stage, that's not significant. Comparing S3 with any of these is significant. That's for MTA width, the thickness measure, not for the parabolic model.
So
Is that what you meant?
Yeah.
Yeah, okay.
Yesterday we saw that with factor reduction, we found breast cancer symptoms with 15 months prior.
Yeah.
So was there any case done with this also? Because preventive is better than finding.
No, we cannot. How can I do that here? Because the babies are premature, the imaging is done, and we get the image. There is no, you cannot go backward for the babies. We don't have images. Oh, the images are taken, I don't know how many times they take the images. What we did, which I don't have here, is we compared the images before and after treatment. Once it is diagnosed, there is the treatment applied by Dr. Els and her colleagues, and there is some expected change. But that happens over time. It doesn't happen immediately. And some of those images were obtained just for a handful of cases. I don't remember if I could check with Faraz's thesis and tell you what exactly was done and how many cases we got. But we didn't have enough cases. So in this case, it is not possible to do something like breast cancer screening, where a woman who is, let's say, 50 years old has gone through the screening program for, let's say, 10 years from the time she was 40, and she would have 5 screening sessions. In this case, there is no such thing. But after treatment, we had a few images. So before and after treatment, we compared. And we saw some changes that would agree with the expectation. but we didn't have enough data to do statistical analysis. So I cannot conclude as we did for the architectural distortion prior mammogram case. It's not possible here. Is that what you asked? Yeah, okay. That possibility is not here.
Any other questions? If there are no questions, we'll stop here.
So I just talk about an linear algebra. Anyway, right, so it's very difficult to give a class after the lunch. Of course, it's very difficult to listen the class after the lunch. So anyway, right. I'll start with the question. What is the goal of the linear algebra? The goal of the linear algebra. The goal of the linear algebra. The goal of linear algebra. The goal is to solve the system of equations. Goal is to solve the system of equations. Ax equal to b. But in linear algebra we talk many things. We talk about vector spaces. We talk about the what do you call, right? The bases, independence, dimensions of the vector spaces, diagonalization of the matrix, eigenvectors of the matrix. We do talk about many things of linear algebra. Sometimes those who teach linear algebra, they miss the connection between the topics that we cover to the Ax equal to b. So our aim is to solve the linear set of equations. Where do you get this? The question is, where do you get this? How do you get this? Where do you find these things? Of course, these system of equations depends upon the application. Suppose, for example, if you want to filter the signal, okay, if you want to remove the noise in the signal coming to the communication system, right? You want to design, say you want to design the filter. Basically, design of the filter means that getting the filter coefficients, right? So what is the input to this? The input to this is the noisy signal. Noisy signal. What you wanted to get at the output is the desired signal. Desired signal. You can form a matrix, a system of equations, something like this. Let's say the desired signal is let's say B. You may want to solve the system of equations something like this, where B is a desired signal and W is the filter parameters, and the A is the data matrix. A is data matrix, right? So W is the coefficient matrix, coefficient vector, and B is the desired signal. So you may want to, you may have to find, right? To find the filter coefficients, you may have to solve the system of equations system of equations Ax equal to b, or AW equal to b. There are the system of equations that you get depends upon the application. Maybe in communication engineering you may find a particular system of equations. In medical imaging you may find a kind of system of equations, and you may find different set of equations in other applications. Now first what we do is that we try to connect. You already studied the vector spaces. Okay. To solve this, we use the vectors, the linear algebra concepts, right? So let us, before that, we just connect what is the relation between the vector spaces and the system of equations. How do you generate the vector spaces with respect to this, with respect to the A, right? What is the connection between the vector spaces to the Ax equal to B? So you may see the column space of A. There are four vector spaces that are connected to the A. One is the column space of A, and the other one is null space of A, and row space of A, and null space of A transpose. There are four spaces that are connected to the matrix. There are four vector spaces that are connected to the A matrix. What is the connection? What is the connection between these spaces and the system of equations? What is the column space here? The column space. The column space. What is the column space? The column space is this. The column space of A is Ax. The column space of A is Ax. What do you mean by this? What do you mean by column space of A? Say for example, a trivial case, let's say the matrix is this. What do you mean by, let's say X is a two-dimensional vector. What do you mean by this into this? What is Ax? What is the column space? The column space is nothing but the linear combinations of A. The column space is nothing but the linear combination of the vectors. Now you tell me, what is the column space for this matrix? 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 If I take the linear combination of this vector, what is that you are going to see? What kind of vectors that you see? What is that you are going to fill up? Suppose if my x equal to where x takes the value from the real line and y takes the value from the real line. I mean, just I'm diluting to the notations and all, but you just consider the x and y are the values from the real line. Any value. Okay. It can be, if x equal to 0 and y equal to 0, what is the vector? What is the vector? 0, 0. 0, 0 vector is in the column space of A. 0 vector is in the column space of A. 0 vector is in the column space of A. Say x equal to 1 and y equal to 0. And this vector also is in the column space of A. X equivalent to 0 and y equivalent to 1. This also is in the column space. X equivalent to 0.5, y equivalent to 0.5. What is that vector? The 0.5, 0.5. 0.5 also is in the column, the column space of A. Now, you tell me what is the column space of A here? The column space of A is the entire R2. Entire R2. Now you are equating the column space. Now what you wanted to have is, we wanted to equate this column space to the B. Ax equivalent to B. Now if you want to have a solution, if you want to equate this to this, the B should be coming from what? B should be coming from what? You want to equate, so this is not there, this is not there. Now you want to equate this to B. Want to equate this to B. Now B should come from, if you want to equate that, there is a bunch of vectors here, bunch of vectors in the column space of A, right? So that is given by Ax. Now you are bringing another vector which must be equivalent to Ax. Where the B should come from? The B should come from column space of A. So the first thing is, the solution exists. The solution exists if B belongs to the column space. If B is coming from the column space of A, then you will have the solution. If B is not coming from the column space of A, then you will not have the solution. Now for this matrix, if my A is this, let's say my A is this, if my A is this, you would see that for any B you will have the solution. The reason is, the B that you are going to put here is from the column space of A. Any B you take, it may be 1, 2 or 3, 4 or anything that you bring in, B is coming from the column space of A. If B is coming from the column space of A, then there is a solution. So the first condition is, on the right, if you want to have the solution, the B must be coming from the column space of A. Right? So the B must be, suppose you have the matrix something like this. How many of you say that this system of equations have solution? What is the reason that you don't have solution? What is the reason that you don't have solution here? What is the reason that you don't have solution? What is the reason that you don't have solution? 1, 2, 0. Do you have a solution for that? What is the column space of that? What is the column space of that? Can you tell me what is the column space of that? What is the column space of that? What is the column space? The column space is the linear combination of the vectors, column vectors, right? You take the linear combination and check what is the column space. This is the, this is the column space. What is that column space? What is that column space? In the R2, what is the column space? It's not the R square, it is something else. What is that? If I take the linear combination of this, what kind of, see, suppose like say x equivalent to 0 or x equivalent to 1, y equivalent to 0, what is that you get? 1 0. Okay. Say x equivalent to 1 and y equivalent to 1, what is that you get? X equivalent to 1 and y equivalent to 1, what is that you get? You get 3 0, right? Whatever may be the right, whatever may be the the values, the x and y values, what is the y component here? What is the y component? The y component is 0. The y component is always 0. Only you have the x component. Now you tell me what are the vectors this is going to fill up. This is what? Where the vectors you find? X-axis. Now your vector space is x-axis. The column space is a line, x-axis. Your column space is x-axis. Your column space is a x-axis. Right? Now look at the B. B is, what is the B here? The B is this, right? Maybe little this one, okay, right? So this is 2 1. Your B is this. Your B is this. B is coming from the column space of A. B is from this x-axis. No, B is from somewhere else. B is not from the x-axis. Suppose if I change this vector, if I change this B vector, if I change the B vector as 3 0, do you have a solution? You have a solution for this? Yes. What is the reason here? What is the reason that you have solution? The B is coming from the x-axis. B is coming from the column space of A. So the first condition, right, to have a solution is the B must be coming from the B must come from the column space of A. For a particular B, if you have the solution, then that is called the particular solution. You heard about the particular solution? Particular solution and homogeneous solution. Say for particular B, right, you have solution. If B is coming from the column space of A, you will have the solution. That is called the particular solution. That is not the only solution. There is another solution that would exist. There are like when other solutions exist is if there is a null space of A. If there is a null space of A. What do you mean by null space of A? What is that? What do you find? Null space consists of bunch of vectors. Null space consists of a bunch of vectors. Right? So you find the vectors. What are these vectors? These vectors are solution to the Ax equal to 0. Say xn. So these are the xn. Let's say the solution that you get for the particular B is xp. Now I combine these two solutions. Will it be a solution to the Ax equal to b? Will it be a solution to the Ax equal to b? Will this be a solution to Ax equal to b? Try out, right? So what should we get when I say this is the solution, right? When I multiply that solution with the A, I should get b, right? I multiply A, right? What should I get? I should get, what is the Ax b? B. And this is, what is this? Xn is a vector which is a solution to this, right? Xn is a solution to this, Ax equal to 0. If, right, what is that, A into Xn, if this is a solution to the Ax equal to 0, right? So this is 0, so this is equal to b. In addition to xp, particular solution, there are many other solutions. See, xp is not only the solution, right? There are, right, because of this, you would see the system of equations will have infinite solutions. If this is not there, only you will have if the solution exists, if the B is coming from the column space of A, you will have only one solution, unique solution. So what are the possible solutions we have here for the system of equations? Unique solution and no solution and one more? Huh? If multiple solutions exist, there are infinite solutions. Okay, right? These are the three possible solutions we have. When do you have the unique solution? You will have the unique solution. The condition to have a solution is, the condition to have a solution is, right, the first condition is B should come from the column space of A. When you say a system has a solution, B must be coming from the column space of A. Then you can tell about whether this has a unique solution or infinite solution by looking at the null space. If you have a null space, then you will have if, right, let's say n of A. If n of A exists, then infinite solutions. If B is not from the column space of A, then no solution. This is the first condition to have no solution. If the B is coming from the column space of A, then you need to check the second condition to say that whether system of equations having a unique solution or infinite solutions. If there exists a null space of A, then you will have the infinite solutions. So for example, let us have, okay, trivial. See, when you don't understand, anything, you just take the trivial example. You'll understand everything. Okay, just take. How many say that? How many solutions this system of equations has? Unique or no solution or infinite solutions? Huh? Unique solution. The reason is that the B is from the column space of A. The particular solution exists, right? And if you want to if you want to check this, right? So you need to check whether this system of equations having infinite solutions or not. When do you say this system of equations have infinite solution? How do you check that? You need to check. You need to check that this system of equations have a solution or not. Can we have a solution for that? Can we have a solution? Can we have say solution for this system of equations? No, right? Other than 0, 0 vector, you don't have any other solution. Other than 0 vector, you don't have other solutions. So no, null space vectors. No, right? No vector other than 0 vector would give you, the 0 vector here. There's no null space here. So the system of equations have a unique solutions. Unique solution. Now can you give me the example where the system of equations have infinite solutions? Okay, right? So I'll give you right example. The same example you take. Okay. Now, what is the particular solution here? What is the particular solution? You can straight away tell, right? What is the particular solution here? X into 0, x into this, y into this. If x equal to 0, y equal to 1, then how do you write this? This you can write it as x into 1 0 plus y into 2 0. Right? If you want to get the b, this other side, your x must be 0 and y must be 1. Right? So this is my solution. This is my solution. X is 0 and y equivalent to 1. Is that fine? Is that a solution? Right? That is a solution, right? For this b, see one of the vector in the column space is 2 0. See the 2 0 is appearing here itself in the the columns. So you can say that you leave this, right? How do you see what is this a into x? A into x is basically x into this plus y into this. You can write like that. You can write this is the linear combination of the vectors. Now this must be equal to 2 0. When this will be equal to, this linear combination is equal to 2 0. If x equal to 0 and y equal to 1, you have the right. You have the solution. You have right. If this x equal to 0 and y equal to 1, this entire thing is equal to this. You have the solution. Particular solution you have. The particular solution you have. What is xp? xp is 0 1. Can you find the null space solutions for this? What is the null space solution to this? What is the null space solution to this? 0 0, right? So here, what is that? How do you get it? Can you give me any null space solution? Any vector which gives you 0, 0 other side. What is that? Sir? Correct, right? So you can write this, right? So you say x equivalent to, say x equivalent to 2, x equivalent to minus 2, y equivalent to 1. That's the solution to the x equivalent to 0. Is the only solution? Is the only null space solution? What you can do? The scaled version of that. The scaled version of this is also solution, right? The scaled version of this also solution. Now you add this to the particular solution, right? This is xp plus xn, right? What is the xn here is that 0, 1 c into minus 2 into 1. You see how many solutions you get, where c is the constant, okay? C is the value from the real life. C is a constant. You can take any value. It doesn't matter what the the value of c here. But c into this is a solution to the, you multiply c here, right? Take here minus 2, 1. It doesn't matter the c is here or not. See, always it will be 0, 0. Now how many solutions you have? Infinite. This is the example for the infinite solutions. Okay. Okay, right? So see, you would see there are different types of system of equations, right, in the literature. How do you differentiate that? Based on the rank of the matrix. Suppose, let's say A is m by n matrix, and the rank of the matrix is R, which is equal to m is equal to n. Right? This is one kind of system of equations. One kind of a system of equations. The second one is, right, A is m by n matrix, and the rank of A is equivalent to n, and which is less than m. Okay, this is called the full rank matrix. The system of equations, the number of equations, the number of variables in the system equation depends upon the rank of the matrix. The rank of the matrix. It depends upon right. Of course, this, right, m by n. But the solutions of the system of equations depends upon the rank of the matrix. The solution of this system of equations depends upon the rank of the matrix. So these are of course you can differentiate, you can divide this system of equations based on the rank of the matrix. Right? So the other possibility is that other system of equations, right, are possible where the rank of the matrix is R, which is equivalent to m and which is less than n. And the fourth one is the rank of A is R, which is less than M comma M. For the practical applications, often you don't see this scenario. You don't see this. But in communication problems, we assume that we have this situation where the rank of the matrix is n. You can say that this is which is a full rank matrix. So you may find something like this. You may find the this, and of course right, you say that 0 also. Okay. Yeah, so you see that, right? So you don't take this. Then if you don't take this, let's say this other side is okay, right? This is one possibility. Right? This is Ax equivalent to B, where A is m by n size, right? Where A is 3 by 2, and the rank of A is what? What is the rank of A? 2. The rank of A is 2. Rank of A is 2, which is equivalent to the number of columns. Number of columns. If this is the scenario, then this is called the full column rank. Full column rank. This is a particular type of system of equations. These system of equations often you find in communication engineering, communication engineering problems. For example, if you want to design get the the filter coefficients of the linear filter. Okay. So we assume that here in practical it won't be like this, but we assume that the A has the full column rank. We assume that A has a full column rank. This is one scenario that you see. Okay. But you will understand this scenario if I give the example. If I draw this, right, I can derive this system of equations, right, from the problem of designing the Wiener filter, the problem of designing the Wiener filter. We can always right, but we don't have time, so I cannot show you how you can form the system of equations for the given problem. Okay. So there are cases, right? So you may have to solve the system of equations of this form, or you may have to solve the system of equations of this. You may have to solve the system of equation like this. What is the rank of that? Can anybody tell me what is the rank of that? I just flipped that, okay? This matrix I just flipped. Okay. So what is the rank of that matrix? 2, right? A is 2, which is equivalent to the number of rows. The number of rows. This is one case. Often this case you find in medical imaging problems. This is called the over-determined system, and this is under-determined system. Usually, right, these are all called, right, in the imaging problem, this is called the measurements, and these are called the unknowns, and this is the matrix obtained from the linear operator. Right, it depends actually. Depends upon, this A depends upon the linear operator that you use, okay. It depends on the linear operator that you use. Okay, the linear operator. In these two cases, right, this other case, the special case, we'll come to that, okay. So look at these two cases. These system of equations have a particular, a special case of solutions. By looking at the B, what is the solution to this? What is the solution to this? By looking at the B, it doesn't have a solution. By looking at the B is not come from the column space of A, no solution. No solution. Now how many solutions it has? For a particular B, right? B is here B is coming from the column space of A, and also this system of equations have and this system of equations may have a solution, unique solution, or no solution. But this system of equations have an infinite solution because the B always comes from the column space of A, and in addition there is the null space exists. So here infinite solutions. One case is from communication engineering problem, and one case is from the medical imaging problem. You may have the number of measurements. What happens in a medical imaging problem, most of the cases the number of unknowns more than the measurements that you take. So always you have the underdetermined system in the medical imaging problem. So you will have infinite solutions in this case. In communication, most of the time you don't have solution because in communication problem this is the desired signal, and these are the coefficients, and this is the data matrix. Data matrix. You will not have most of the time you cannot match, right? You cannot match. This is actually, this data matrix is formed by the noisy data. You cannot match this AX equivalent to B. The assumption is that you cannot match this with the B. You cannot match AX with the desired signal. That is the assumption that we make. So here, suppose if you are able to match, if you know that if you are able to match with the B, the desired signal, then you will have the unique solution. Most of the time it doesn't have a solution. No solution. But here If this is the scenario, always you have infinite solutions. So if you look at the fourth case, yes, yes.
So what causes the other system, the communication system, to be overdetermined? Are we making more measurements?
More measurement. See,
And
basically,
noisy.
yes, noisy. See, these measurements are more than the unknowns. Why, you will have the overdetermined? Because the measurements here. So this is the desired signal. The number of samples that you see in the, right? Usually, right? See, this is maybe the problem from the design of the design of the Wiener filter. The parameters that we want to find for the Wiener filter is, the number of parameters that we want to find for the Wiener filter is less than the number of samples that we get, that we receive. That is the reason you would see this is the overdetermined system, right? And this is the underdetermined system. Means the number of measurements that you get is always less than the number of unknowns. The assumption, it's not that right, you always have the infinite solution. The assumption is that this is the full row rank matrix. If it is a full row rank matrix, then you have the infinite solution. So there is a special case. You can see that if the matrix is this, suppose, right, you have the something called, right, so you see what is the case? Let's say you have you take all zeros here, and then here you take, okay. Now you look at this system. Now you look at the system. Z, let's say K, right? It won't be, it won't be a sparse matrix. Just I'm giving the example, okay? It will have full of course, you find the values which are redundant to, other values, okay? You see that, most of the, you don't find zeros here. You find other vectors, but the vectors are, highly, you say that the vectors are dependent, okay? So this is the case. What is the rank of this matrix? Can anybody tell me what is the rank of this matrix? The rank of it. It says 3. 2. Which is less than, right? What is that? 4 comma 4. This is a special case, okay? People wanted to get the solution for all these cases. So the first case is, this is a behaved system of equations, where the rank of the matrix is, the number of columns and rows is a well behaved system, okay. We don't have any problem with this. What is the solution in this case? What is the solution in this case? A inverse B. You don't have any problem with the, right, the first case. But the problem we have is for the second case, third case and fourth case. The problem we have for this case and this case. How do you get the solution? So for the first case, I don't want to know we require one more class to explain everything. But I just give you overall what is the solution we will have, okay. So in this case, that this system of equations are well behaved. So in this case, there is something called, right, you say that for this case A inverse exists. When I say A inverse exists, it has a left inverse and right inverse. It has a left inverse and right inverse for the well-behaved case. For the second case, this case, the left inverse exists. No right inverse. No right inverse. Only left inverse exists. In this case, you have a right inverse and in this you don't have the left inverse. So the left inverse saves this problem. The solution to this is to do with the left inverse here. The solution to this one is to do with the right inverse, not the left inverse. And here, this case, we don't have left inverse or right inverse. Gone case. Okay, we don't have, we can't use left inverse or right. But this, you can use a particular inverse. You know that. Okay, what is that inverse that we can use here to solve the problems? So pseudo inverse. Right? You heard about the pseudo inverse? This is spelling. Pseudo inverse, is that correct? A dagger. Okay, this is dagger is something, I don't know how to. So a dagger. For this problem, the solution is this. For this problem, the solution is this. For this problem, we combine these two, and the solution is to do with the A transpose and then A transpose A. It is to do with the eigenvalues of those two matrices. The solution to this is a pseudo inverse. It is to do with the, you heard about this SVD, something called SVD, singular value decomposition. Okay, so yeah. Why we call it as the left inverse and why this is called the right inverse? I'll just give you that. I cannot show you how do you how I cannot in this class I cannot do that. Okay, I cannot do that. What is that? I cannot prove that this is a solution to this problem. Okay, but at least I would say that this is a this is, you can see that from this solution there is possibility that you can have the left inverse for the A. By looking at this solution, we can say that there is a right inverse for the A. So let me I'll do it here. Now we know that the least square solution is this, right? Now what I do is that I take this part and multiply this with, this is the part with A. What would I get? A transpose A inverse A transpose A. What is that you get? Of course, we have to make one more assumption. Assumption is that they should be invertible. Of course, for this case, this is invertible. Okay. Now A transpose A inverse A transpose A. What is that? Identity, right? Then what you would say about this factor? Since this is sitting on the right, left side of A, then you would say that this is the left inverse. And look at this solution. Look at this solution. I'll just do it here. What is the solution? The solution is I take this solution, then what I do is that, is the solution? Yeah, right, so I just keep this term on the right side of the A. Then what is this? I. So the assumption is that this is invertible. Okay. See, for this case, the A transpose is invertible. Now, since it is sitting on the right side of A, this is called the right inverse. If you want a solution to this, then you combine the left inverse and right inverse. So you have to work with, here you observe that for this solution we work with the A transpose A, and for this solution we work with the A transpose. So if you want to have the solution, you have to work with the two matrices, which are A transpose and A transpose A. Okay, so we don't have time. I just So do you have any questions from this?
The A transpose A or A transpose is simply to convert a non-square matrix to a square. So
Yes, correct. Yeah. And assumption is that if this is the scenario, right? If the rank of the matrix is 2, which is equal to the number of columns, then always A transpose A is invertible. That's why you could able to do the inverse here. You could able to get the solution like this. This is called what is this called? You have seen anytime this one in SAR's presentations. Have you seen anytime this solution? You have seen, right? Least square solution. Is there least square solution? But this system of equations will have infinite solutions. If you have infinite solution, what is the solution that you take? What is the solution you take? See, in this case, no solution. Okay, right? You take the best out of that. Best solution which minimize the error. Okay, but here we have so many solutions, infinite solutions we have. But what is the solution that we take? What is the solution that we take? Any guess? I'll do it here. What is the solution that we take? Put the constraints. You have to put the constraints. It will become another optimization problem. So what is that you take is, out of infinite solutions, you take the solution which is near to the origin. So how do you formulate that? So you minimize this subjected to Ax equal to B. And the solution to this is this. Solution to this is this. And this solution gives you, the solution out of, infinite solution, which is, near to the origin. Okay, so I think, I'll stop here because, I don't want to get into, right? Maybe if you want me to take, one more class, I'll take one more class and I'll talk about the pseudo inverse, right here. But pseudo inverse is to do with the SVD of the A. You heard about the singular value decomposition, right? So when I use, when I use the singular, the pseudo inverse will take to, to the solution depends upon the case we have here. So in this case, in the fourth case, what are possible solutions that we can have in the fourth case? In the fourth case, the possibility is that no solution and infinite solutions. These are the two possible solutions for this. When you don't have solution, this pseudo inverse would take to the least square. When you have solution, infinite solution, the pseudo inverse will take you to this solution. The reason is that the pseudo inverse involves A transpose A and A transpose. The pseudo inverse takes you to the either this solution or this solution, depending upon the the case here, depending upon the rank. If the rank of depending upon the solution that we have here, if there no solution, then the pseudo inverse will take you to the least square. If there are infinite solutions, right, the pseudo inverse would take you to this solution. So,
an observation, but please tell me if I'm wrong. You mentioned that in this case, in communication, we have an overdetermined system, but that's by design. The filter coefficients are fewer in number than the data samples, signal samples. That's understandable. But in the other case, in
imaging and all, yeah.
Yeah. For example, in algebraic reconstruction,
Yes.
the image size is much larger than the
Image, the unknowns actually. Yeah, X-ray measurements, right? Yeah. Yes.
There, those considerations come into play that will limit the number of measurements.
Number of measurements, correct.
Hence, your
System is underdetermined, yes.
Is that correct?
Correct, sir. Yes. Yeah. So, do you have any doubts, if you want me? It's fine, right? This is the summary of linear algebra. I mean, I just like in one class, I covered entire linear algebra. See, this would I talk about this class. I talk about in 40 lectures, around 40 lectures. In 40 lectures in one lecture here. So this is the basic knowledge that we need to have, right? So before you take up any of the course. Right. So any doubts from this solution to the system of equations? Sorry, you may not, I don't know how many of you got the information. So you need to have a little basics of that. So you are telling, so you are from? No, that. No. Second year. BTech. You already done, right? Part of this.
Yes, sir, I have.
Okay. So. Yes. Yeah.
So we'll continue where we left study class. So I hope just quick review. So classification task, as we'll be using the image based classification where the model is start from VG16, 19, then GoogleNet, InceptionNet, ResNet. So ResNet is a focus because it's very important model used for various real-time application as well as developing core application in the medical field as well as other field as well. And then DenseNet, more deeper model, then Inception ResNet, and then other models which related in the medical field, and then finally LiverNet, 2.x, RenalNet, and so on. And these things already we discussed quickly. So, so this was the as a traditional way of developing a CAD system which we discussed yesterday. This you also have seen that all the process. So here you see that why that some pre-processing required in case of histopathology images. Same liver organ is scanned by two macroscopy over. So first is called DP70, which is Olympus macroscope. Second is called Filia 2. Same organ is scanned from the two different scanner. So you can see there is a color variations. So if pathologists want to take any diagnostic decision based on these images, their always decision will be wrong, right? So we need to do some sort of color normalization so that the color problem in the macroscopy should be resolved it, right? And this you have seen that liver type SCC. This also we have seen yesterday. So we supposed to start from here as a more deeper of the architecture for classification of liver cancer grades from histopathology images. So this also we have seen yesterday as steps for building a deep learning model, right? Quick review: collect data set from the hospital, or if you get some public data set, it is good because already you have benchmark models and already well established data set. Then try to capture the additional data set from your nearby hospital and then get result validated by the radiologist or your histopathologist or ophthalmologist and so on. Then understanding pre-processing data is must. Creating deep learning model, training of deep learning model, testing of deep learning model, performance evaluation. So here precision recall, F1 score, right? All the matrix analysis has to be done of a trained model. And then testing of a model on the new samples. This is very important because unless if you test the model on the new patient data, the model will not be generalizations. And also you need to think about for generalization of a model, try to get a multiple hospital data, because the data you are capturing, what other person is capturing, there may be some slight variations. If you take the two hospital data, mix it, train a model, right, and then you test it on this. So the model itself will be having the multiple way of the scanning of data, right? So that will also is other good options will be tried to do that as there. So when comes the implementation, so implementation using deep learning, these are the various framework. You can use Keras framework using TensorFlow, and then you can do for only Keras framework using TensorFlow library, PyTorch framework using PyTorch deep learning library. So these are the steps which already some of things is discussed today, but quick see for any binary classification in the sense that whenever you are trying to find out detect the cancerous or non-cancer tumor, right? So in that case, while designing or the building model using any library, keep in mind, right, ReLU activations or better than ReLU activations, Leaky ReLU, P ReLU, SeLU, JLU, right? Advanced activations you try to use that. And the loss function is binary cross entropy. But apart from the binary cross entropy, you can use other loss functions. For example, you can use even the variants of this called weighted cross entropy, is there balance cross entropy, and then Dias loss can be used, focal loss can be used, right? Loss softmax loss functions can be used, right? So, and combination of as well, right? You can do as well, combine loss functions, right? And then, of course, you select one particular optimizer, anyone. ADAM is a prefer in all the, for advanced level of research, but you can do for try RADAM or some new ADAM, new the optimizer introduced for the deep learning. And of course, output layer R base keep the sigmoid activation functions, because the sigmoid activation functions here that give you the probability for the 0 class and probability for the 1 class, right? So again, once you get the probability, then again you have to go for the thresholding operation to get the exact class, right? 0 class and 1 class, right? So if probability close to 0, then belongs to the 0 class, and if the probability is close to 1, then that will belongs to the predicted class will be 1. And sometime may happen, it may be false also predictions, right? So that need to be checked, right, by looking that whether what was the ground truth, what is the predicted, is it same or any difference is there. Then in case of multi-class, so again keeping the first and third the constant, only change on the loss functions. So loss functions will be here critical cross entropy as a loss. I mean, this is a standard loss which everybody start using from this loss function, but you can also use focal loss. So focal loss is used for both, for binary classification task as well as for multi-class classification task. Likewise, you can use the loss softmax, right? That also used for the both binary as well as for multi-class classification task, right? Then output layer, again you have to use the softmax activation, right? So in softmax, as I told you, using, but as a additional operations will be doing the call argmax. So argmax will be using, because it give you the probability of the classes, right? So if you have the 10 classes, so that output will be y hat, which will be the 10 probabilities, right? So here it may be some values, so you will get the 10 probabilities, right? Then you need to use the final class. So y underscore class, predicted class will be, that will be arg max of y hat. So what it is, it is going to do, it does here, just scan the column wise, and if let's say this column is having the highest probability, then it will take this belongs to this particular position class, right? 0, 1, 2, 3, this is 4, so it will be 4 class predicted, right? So this as a additional operations, right? After getting the y hat, you have to do get a specific class label, right? And here just the model which we have designed in the 2021 LeverNet models. So this is a complete, this is general methodology, I would say, right? Now it is applicable for any kind of cancer grading. It may be liver, it may be kidney, it may be colon, right? Any kind of this. So depend on the classes, it will be changes. As a study I told you, because in the liver cancer grading, we were having the limited number of samples for higher grade. So we try to class subtype 3 be just grade 3 and grade 4 we need to just merge it, right? To train the models, right? And type 1 we were able to get the sufficient sample, type 2 also the sufficient sample, but type 3 and 4 was the problem, so that's why we merge it, make it as a total 4 class classification problem, right? And before going to the deeper architecture, right, need to understand that as a BG16 architecture, then resonate, and then at least, because API, whenever try to use the TensorFlow Lab API, there the already created model is start from the BG16. So you can test also BG16, and then you can go for resonate and so on, like advanced models, whatever is there as a classification model. So BG16, this model was introduced in 2014 by the Oxford Geometry Group. That's called here visual geometry group. VG stand for visual geometry groups. It's Oxford, the university. And 16 stand for the 16 baited layer architecture, which includes 16 convolution layers plus 13 fully connected layers, FC layer 3. So total 13 plus 3, that's combinations, right? So here you see that this is input data image data, which is color. Then here you see that convolution layers, 2 set of convolution, then max pooling, 2 set of convolutions, max pooling, 3 set of convolution layers, then max pooling, 3 set of convolutions, max pooling, 3 set of convolution, and then here again one max pooling, then 1 cross 1, that is converting as a finally one hot, you flatten it, and then 2 fully connected layers will be there. Finally our last output will be a 1000 nodes, because this particular model is for design, and this was a challenge of ImageNet large scale visual recognition challenge in that was again conducted 2024. It started in 2012, Alexander was the winner, but in between like 2012 and 14 the variants of the Alexander also introduced little bit minor modifications, but this was the one of the, I would say, in 14 was the best model, because this model is having the generalizations in the sense that they are using all the convolution layers, they are using the 3x3 kernels, and max pooling they are using the 2x2 kernel size, and the stride they are making as a wherever convolution stride is 1, right? But AlexNet what was there, they are using the different stride as well and different kernel size, so that was a major problem. So they make it a streamline the model here, they bend little more deeper, and uniformity they maintain that whenever convolutions means 3x3 kernels will be used. Okay, so whole the VG16 architectures you can split into 2 parts, that's called feature extractor and classification part. So if you see that here from here to here, right, that's called feature extractor part, and from here to here is called 3 layer 3, that will be called as a classification part, right? So in feature extractor you can see the very clearly in this slides, input data is 224 comma 2 cross 224 cross 3 color image, and then doing the 2D convolution, right, with the kernel size of 3x3, right, and you are getting, and here also using the zero padding, right? Study I told you concept of zero padding, right? So zero padding, so after convol we are getting the 224 into 64. 64 means at this particular layer they were using the 64 number of filters to do a 2D convolution operations, right? That means this particular layer 64 different feature were extracted, right? And since there are 2 consecutive convolution layers, whenever is a consecutive convolution layers you have to use, make sure the number of filter remains same, number of kernels should be same, don't change that. Okay, so again 3x3 convolution layers, again the number of filter remain the same, right? And then max pooling. So max pooling, as told you, the idea is just do the subsampling, right? So earlier the size whatever was there 224 cross 224 divided by 2 become 112 cross 112 cross 64, right? So this we got as here this first step. Then again 2 set of convolutions. Now you see here using 128 number of filters, right? Kernel size remains same 3x3, but number of filter is increased 128 120 because these are 2 consecutive convolution layer, right? And then max pooling. Then here 3 consecutive convolution layers. So here 256 256 2, each layer convolution layers they are using the 256 cross 256. That means they are extracting the each layer 256 different feature values. Okay, then again this will continue the same pattern here, right? So finally you see the 256 512 and 512, these are having maximum 512 cross 512 kernel number of filters, don't go beyond that. And this was required because this was trained on the that imaginary data set which were having the millions of the images, right? So that's very high volume data, right? But if you are trying to same model for your project work, right, your task, you should follow the structure. You need not to follow the same number of like this filters. This should be get fine tuned based on your problem statement, right? You can start maybe 32 or 16 right now, and then you can slowly increase 16, 32, 64, 128, like that you can go, right? And may not be even this 16 layer architecture may not be also needed. You can customize it. You can make it as a 13 VG16 also, right? VG16 is a like unique thing is that uniform pattern, right? Convolution 3 cross 3, right? And the stride is 1 fix, right? So you can do the same things, right? So I hope this clear feature extractor part. This is the same things was there in feature extractor. All the things a little in bigger way you can see that, and each layer you can calculate the width and height of the convolve feature map by using the formula study what we discussed that, okay? And then next is the fully connected layers. So fully connected layers here, so first need to do flatten, right? To do the flatten study I told you very simple concept, 2D matrix need to convert as a column vector, because this fully connected layers is nothing, it's a ANN, artificial neural network, right, which always accept data in the column vector form, right? So we need to do flatten operation. Then after that dense layer, so dense layer here using 4096, that means this much node required only for imaginary data set. If you are using your own data set, this much node not enough, not needed. You can use maybe 512, that will be enough, or even the 256 nodes, right? Because this much feature going to connect this many nodes, like see that, okay? And then dropout. So dropout basically used to, during the training what happened, and it may be what I say that dropout always use a percentage, right? So it may be like 25% or maybe 50%, right? So what happened dropout, if you are using 50%, so 50% node, if you write drop point 0.50, means during the training randomly 50% nodes become inactive. Out of how many? Out of 4096. If you say 0.25, means 25% of the 406 nodes that become inactive right now. So dropout is necessary to overcome the limitation of overfitting problems, right? So keep in mind that the role of the dropout here. Then next here again the dense layer means nothing's your ANN part, right? And here again the same number of nodes used. Then again dropout, and then last you see dense layer, which is nothing the softmax, right? So softmax with the 1000, so you will get the on imagery data set having the 1000 classes of that, okay? So this is just as a the concept of the this VG16 architecture. It's very important. When you start learning, so start from the LeanNet 5, LexNet, and then VG16, go gradually. So increase the complexity gradually, and then coming to the VG19 model. So VG19 is nothing, is an extension of the VG16 only. Here 16 convolution layer and 3 fully connected layers, right? So that total having the 19 weighted layer. I hope that makes sense, okay? So you can also try VG16, VG19, depend on the data set, whatever you have, your project problem you are working that, right? Then this is called residual network, right? ResNet stands for residual network. It's very important and frequently used for many applications. Also now, whenever you do the segmentation task, as an encoder side, it is also used as a like pretain, right? As a encoder, pretain features that are used from the ResNet there also. So it's very important ResNet as far as architecture is concerned. So there are various variants of the ResNet model architectures. That's called ResNet 18, ResNet 34, ResNet 50, ResNet 101, ResNet 152, right? But this is most important, right? Why ResNet 18, 34 are necessary? Because when you start learning, right, you have to create yourself everything, right? So creating 50 layer, it will take more time as a concept is concerned, right now. But creating 18 layer architecture is easy, right? Like once you created 16 layer architecture, 16-bit layer, you can easily create the 18 layer architectures, will not a problem. 34 also you can create, right, will not a problem, right? 50, you have to spend more time for, creating the model, right? Likewise, 101 you require more times, right? 150 more. So these are the variants are available as far as residual network is concerned, right? And then this is already have ResNet 50 with pretrain also available using the TensorFlow that package, right? You can do on the pretrain means transfer learning, right? You can use on the ImageNet bit also, you can work on that. So this case you see that different challenge. So like it started from the 10, 11, 12 where AlexNet was, right, played a big roles, 8 layer architectures. Then it was the extension of AlexNet model that was also included, and then VG16 as a challenge. So in 14 they were the winner, then GoogleNet, then ResNet, right? So ResNet was introduced 2015, right? But they were again the winner of the this IELSVC challenge, right? ImageNet large scale visual recognition challenge, that's called IELSVRC challenge, right? And see that they were having even the smallest parameter as well, right? Now 3.57, right? Where this, if you see that here, right, different layer, 19 layer here also was there, 16 layers, then 22 layers, right? So gradually that layers is increasing, weighted layer, right? But if you also see, the number of parameter is not increasing, right? So that means layer is increasing, but the complexity of the model is not increasing. Performance is increasing. So whenever you as a researcher, if you are trying to design a new model, always keep in mind the model which you are designing should be a light model, less number of parameter, and also that give you the best performance in the benchmark. Say you are doing research in 2015 of 25. So in 25, if you are designing the model, should be better than the model which was designed in 2014, 2024 with the similar task or the same data set, right? So some benchmark data set you need to see which already published, well established, and that you take as a for generalization of the model, and you can create even the new data set. So your model should be giving the best result on the 2 at least data set, minimum 2 nowadays. Otherwise very difficult to get your paper published in a good impact factor journal, right? I hope that's fine. Okay. So let's all that. It's a very popular models. Let's move on that. So one thing is important in the ResNet called skip connections, right? So skip connection is very important, which play a significant role, and they have 2 important things. Like skip connection used to elevate the issue of the balancing gradient by setting up the alternate shortcut for the gradient to pass through that. I'll show you first, then come back. So this is what is the plain block, right? We call as without skip connections. And this side, right side figure is called residual block. So residual block here, if you see, this case just doing the skip connections, right? More clearly you see here, this is we have input, weighted layer, ReLU activation, then weighted layer HX. So what we'll do, the residual block, this input is coming, So from here as a identity block, as a functions, also here adding. So whatever the feature extracted with these layers, we are also adding this as a skip connection. Why we are adding that? Because the model also should learn the unity functions, right? And this higher layer, right, at least it should be as good as the like previous layer. It should not be, give you the worst result, right? That's other reasons, right? So this two things, key point is there in the model. Like one, the model help us, skip connection help us to that alleviates the problem of vanishing gradient. Number two, the model also is learning that unity functions as well, right? Now with these skip connections, right? So this is the key things, right, of the residual. Because of this residual, that's why model become called residual network in as a whole. So this block will be using multiple things, when you designed a resonate 18 or 34 or 50, right? So this residual block will be used in multiple times, right? We'll come back more detailed. One thing already you have seen that. So like here you see little more on the refinement of the block. So there is one more concept called batch normalization, right? So batch normalization we call as a pre-activation layer. Always when you say batch normalization, it is nothing, it's a pre-activation layer, in the sense that you all should always use before the activation functions. When designing your model, right, wherever you use in the activation functions, before that you have to put called batch normalization. Why need to use batch normalization? It basically reduces the covariant shift internal, right? In the sense that internal covariate will be there during the training models based on the mean and variance steps. There is a paper published called batch normalization. You can read in 2015, right? Especially on batch normalizations. But in general, the main objective is to improve the training performance, right? Means if you are using batch normalization, your training time get reduced. That's only the objective of using batch normalization as a layer, right? So here input X 3x3 convolution layer, batch normalization ReLU, then again convolutions, then batch normalizations, whatever feature we extracted, then again we doing a skip connection, then ReLU activations, finally give this called residual. This is standard, right? What we discussed previously, right? It is with batch normalizations. And one more things we can do, since we are using unity here, right? Little further you can improve the performance by adding what? Instead of unity functions, you can also add 1x1 convolution layers. Okay? So you will see that the performance of the model get further improved. Okay? But this is a standard residual block, right? Now, which is used that. You can also come up with this, or further you can also modify this by using, instead of the standard convolutions, you can use separable convolutions if your intention is to design light model for object detection task, or you can use the dilated convolutions, right? That will also help you to improve the feature extractions, right? So there are various ways of to modifying the residual block, right? And there are some other concept can be use that, right? So this is because the heart of this was there, right? As a residual in a resident model, this was the main things, right? That was the, and very lot of citations of this paper got it that. This is nothing that similar to what you have seen that, like as a skip connections and then the convert 2D with batch normalization here. Here there was no batch normalization, only convolutions. You can also put in the skip connections convolve and then batch normalizations, right? That will further improve your training performance, right? And if you see that convolution layer 2D, convert 2D, batch normalization ReLU, convert 2D, batch normalization ReLU, convert 2D, batch normalization, and we are adding then applying the ReLU activations, right? If you using here, there is no point of then using there, right? So we are adding here, see here, convolve, batch, both added, and then after that use the ReLU activation functions, right? Keep in mind, don't do mistakes here, right? Always you do after the adding the features. So this is the 2 points I told you as mitigate the problem of balancing gradient by allowing this alternate shortcut path for gradient to flow as well. And they also, the model also allow to learn identity function, which ensure that higher layer will perform at least as good as the lower layer and not worse, right? This is a key point, right? Always keep in the mind why the skip connection use that, okay? And this skip connections is extensively used, as I told you, as a classification model and also in the segmentation model as a backbone point of view also, right? So ResNet 34, the model, and 34 again means there are total 34 bitted layers. So you see this part, you get the idea. So this is VG19 models, right? And then this is a plain 34 layer architectures, right? So start from here input data, and then you get the fully connected layers, average pooling, then fully connected layers, right? Here are 3, but here get changed here. So up to here there is a call 3 cross 3 convolution layers, right? And then average pooling, and then after that dense layer use, right? Now, and this plain layer. Now this is called 34 layer residual network. See that here, from here to, we are using that. Here 2 consecutive, right? Escape connection used, then 2 consecutive convolution layers, then escape connection, like this, like this. This is a standard, 34 layer architecture ResNet right now, okay? Next up. Here also see that, go back, 1, 2, 3 here using, right? Here how many using? 2 using, right? So you can modify right now, but minimum 2 have to use right now. So here also standard they are using 2 base as a ResNet model right now. Some concept I am telling you, you can, when you doing the project work, doing research, you should have some scope to modify the residual block right now, okay? In between some more concept, there is squeeze and excitation block is there. You can also use that in a skip connection, see that what will happen right now. So you have to look at multiple way for modifying the model. To get paper published, at least 2 novelties should be there in your models, in a high level journals, for example transactions or IEEE journals. Until novelty is not there in your architectures, now standard model publishing is very difficult unless you have created completely new data set, and that data set is very useful and very unique data set, right? I hope that able to get it idea. This is a ResNet 34. Same way, right, you can create the ResNet 34 model, ResNet 101 and then 152 models also, other variants also can be created that. This is the same things within a vertical way, nothing else, right? So now this summarizes all the variants of the ResNet, right? So layer name here different, output size 18 layers, 34 layer, 50 layer, 101 layer, 52 layer, right? So first convolve layer 112 cross 112, convolve 2, right, which 56 cross 56, right? And this will be common for all the cases. So here stride 2 will be common. And then when 2 layers, second convolution layers, 18 layers, 3 cross 3 into C into 2 times, means 2 times use this, right? Then next time third convolution layers, this use again 3 cross 3, 128 filter 2 times use. Then fourth, 14 cross 14 output size will be, and here 3 cross 3, 256, 2 times, right? Cross means 2. Same configuration used into 2 times, right? And then 5x means 512 layers here 2 and 2 times use the same models, right? And this having the flops, floating point operations, basically 1.8 to 0.9, 34 layers, this 3 times use, right? 4 times use, 6 times use, 3 times use, this much, that number of the filters, right? If you see 50 layers, 1 into 1, 64, 3 cross 64, 1 into 1, 256, this configuration is used in the 3 times in the models, right? Then 1 cross 1, 120 is right? 3 cross 3, 120 is 1 cross 1, 5 to 4 times used, same blocks, right? Now, so what happen, you can create this block and you can call multiple times. You can just call that, right? Now, residual block. You can create and you can call multiple times with the bearing filters, right? Then 101 layers, you can see that similar way. Then 152 layer residual network architectures you can create, right? So if you know, if you understood this architectures, you can create that. But again, do not waste time for creating models all the time. Once you understand, right, 50 up to 50 models, you try to do something better, right? You design new models, modify other blocks, introduce new feature blocks, and you can come up with the best model right now. Then application of the ResNet model as follows here. You can do handwritten digit recognition, image data set, segmentation task also will be used as a backbone, breast cancer, kidney, all that, like you can do for like binary classification task, you can do multi-class classification tasks like molecular subtype of cancer detections. You can do also use for land use land cover classification, steel surface, and so on, right? So application is vast of this ResNet model, right? So this is like available as a with the framework as like pre-trained. Keras, as I told you, as a framework front end, back end will be a TensorFlow. You can use as a API, and several pre-trained models on the ImageNet data set. Right, so it's easy to build, need not to for various applications. Whenever you do like computer vision task like object detection or some other, right, where you need not to, especially you should careful in a medical field, right. Apart from the medical field, don't worry, try to use maximize the pre-trained model if available, right. That will be save your time and you can do that, right. But of course again, research means something novel, right now. So you have to come up thinking beyond that as well. So here how to resonate with the Keras framework. Step 1, you have to write code, define identity block to transform the CNN into residual and then build the confusion blocks. Step 2, next build a 50 layer ResNet model by combining both blocks. 3, finally you need to train the model required task, and then Keras framework allow you easily to generate a detailed summary of the models, which you can see that 50 layers are not there, right. So this is a doc, TensorFlow API. If you visit that, you can see that what are the applications are available. How will do that? Base model application.resnet50.resnet50. This is the way you have to do, right? If you are calling a resnet 50, if you are doing VG16, you can write here VG16, right? You can also do DenseNet, you can write whatever model you want to use. That way you need not to code from the scratch. You can use that. I mean, one is called base layer, other is called the top layer, right? So base layer you can retain, right? Top layer you can fine tune, that's right. That's good. So base layer you can retain and top layer you can fine tune, or you can create completely the architectures. If you are doing if you are research scholar, I would suggest you have to create, right, models, because once you create you will learn that right now, okay. And when you are creating, you will do mistakes also, right? When you corrected mistakes, definitely there will be, that happiness will be there in your face, right? Then include underscore top means false, right? That means top layer means feature classification layers I am talking, classification part, right? Classification part, we do not want to standard what is used in the API, right? We want to use ourselves, right? We want to fine tune that, okay? Input false, comma, input, and this here bracket, weights equal to none. Weights equal to none means the model will train from the scratch, right? None means, if you say ImageNet, means the weight will be, the starting weight will be the ImageNet weight, right? And then after that only fine tuning the top layers here, right? So here everything will be trained from the scratch. Input underscore shape equal to image height, comma, image width, comma 3. 3 means that color image, right? Okay. And of course, API is everything written, this part is for color image, right? And then, already I told you, this part fine. Then x equal to base underscore model dot output, which is this part you have then x equal to global average pooling 2D. This global average pooling is nothing, it's a kind of flattening operations, this also use, right. This is a faster approach than the flattening, right. Now you can use, then you can use some kind of dropout, here is written 0.7 just for understanding, right. Now you can use, and then finally the prediction equal to dense, number of classes, activation equal to softmax, right. And then model equal to model, inputs equal to base underscore model dot inputs, comma outputs equal to predictions this here, right. So if you want to add one more here, right, if you want to add one more dense layer, you can add, that's not a problem, right. Since in the resonance, so other things, if you see that this is like API, if you click there, I'll show in the lab part, right, all the pre-trained models available are there in the models, right, you can see that, okay. And again this my link, this is a complete classifying on ImageNet classes with the Result 50 data set. So here if you see that we are importing everything like TensorFlow.keras.application.resnet import as a Resnet 50, then TensorFlow.keras pre-processing import image .application.resnet pre-processing underscore input import decode predictions, and then import numpy is this, model equal to Resnet 50, weights equal to ImageNet. That means I am going to work on the pre-trained weights right now. I am not training from the scratch because using the ImageNet weight here. Then give the path, right, and then you load the image, you can convert as a array, then expand dimension, then pre-process, then model.predictx, you can do. This is called complete transfer learning, right. We are not doing anything from our side. Everything is ImageNet, ImageNet data task, right now. And these are the like models which are pre-trained available for the, even more available. This was the old slides, right. In 2021, I would say, prepared that time was there. So exception V16, 19, ResNet, Inception V3, Inception Region V2, MobileNet, DenseNet, NASNet, Mobile V2, and so on, right. So these are the already available baits on the ImageNet baits trained models are available. You can best use of those models for some applications like agriculture applications, doing crop classification. For that case you need not to train, you will not have enough data, right. So you can use these pre-trained models and you can build some solutions for farmer case. So summary about the ResNet as follows here. ResNet is a powerful backbone model that used very frequently in many computer vision tasks. ResNet uses skip connections to add the output from the earlier layer to later layers. This helps mitigate the bias gradient problem. You can also use as a pre-trained Resnet 50 or code it from yourself or in your own private data set, right. It's up to your choice, right. So quick, just 5 minutes more. This is a model which we have designed, already you have seen as well, right. So this model was giving the LiveNet model average test accuracy on KMC data set. This we created 90.93, average test accuracy on TGCA data set. TGCA is a public data set, right. So this also we created, downloaded and created the data set which giving 97.72. Number of parameter was 7396, and then this complete model, if you see here ASPP block, then here bilinear upsampling here, and then all concatenating this here, and then using the different global average pooling, then fully connected batch normalization and so on, then finally able to do that, right. So as far as novelty is not that much level, right, when we were designing, because this was our first task when we were doing in 2021, right. So but later on we felt that the model, the novelty could be improved, the performance can be further enhanced, the complexity can be reduced there, right. Then and this model was nothing extension of this model, right. That was BraceNet what was available, but their model was complex, so we had come up with that simplest model as well. This you can read the paper, this base BraceNet model paper you can read and understand later on. this what we propose that. So this is like as a standard convolutions which already I have told you before study also. One concept called atrose, 2D atrose convolutions, which called dilate convolutions. So here whatever formula is there, xi plus r dot multiply m comma j plus r dot n w m common. W is a filter or the kernel, and here the input data. So r is basically the rate, different rates, dilation rates. So dilation rate if you depicted in right side, if you see here. So here 1 cross 1 conversion filter is 1. So here the rate equal to 2. 2 means that 1, basically the main idea of using the atrose convolution is to improve to increase the field of view, right? FOV, field of view, right? So field of view, how will increase that? By inserting the zeros between the samples here, right? Features here. So if 3 cross 3 kernels, when rate equal to 2, if you see that between 2 feature samples, right, that one gap is created or the zero is filled, right? Now likewise 3, here 2 will be like 6, 5 the zeros will be inserted, right, both x and y directions, and 8 that means 7 that zeros will be inserted between that. So this way increase the field of view, right? And then after all this you need to do calculate all the feature values and then use the 1 cross 1 convolutions. That's how it help us to improve the performance of the model which we design called LiverNet 2. And also use some of the like convolutional block attention modules. Paper is there, you can read this, you can read that more on this. This was the one concept used. This is a data set which we use that. Total we were having basically 141 slides which we got from the KMC, Kasturba Medical College, Mangalore, with a different patient belonging to 3 subtype of the liver: SCC tumor, solid tissue, primary tumor and recurrent tumor. This is called TGCA. TGCA is a public data set. Very libraries there, you can download on the US, there are repositories there. And then each size of each pixel is 0.0 to 2.5. 0.25 macron. This is nothing, is resolution basically, right? Resolution of the pixels. Normal slides considered as like this here: subtype 0, primary tumor subtype 1, recurrent tumor type 2. So in TGCA only 3 are there, right? Now, not more that. Then KMC dataset which we created, we got 256 original slides from the different patient, each of having the size of 1920 cross 40, belonging to 4 subtype of liver. And here the resolution was the 3.69 cross micrometers, okay? And this data set has been annotated clinically by pathologist KMC, Mangalore, Mahe, Manipal, Karnataka. 70 slides are used subtype 0, 80 slides for 1, 83 slides for the 2, and 24 slides for the subtype 3, right? And then we also did some random patches of this, obtained from the slides, and we did some patches, random 5 patches from the each cases, and created the data set as well. And then we did some training, like also we did 5-volt cross validation techniques on the both the data set, TGC as well as KMC data set. And the loss we use here, you see that loss functions, right? And also use some regularizations as well here. This L, then loss finally this part. And lambda is used in our experiment is 0.003. Optimizer Adam, learning rate use here 0.001, and also our learning rate scheduler also scheme, because it will reduce after like 5 patient, like 5 epochs or 10 epochs. If not increasing, reduce the learning rate further, right? Changes. I mean this change by factor of this point exponential e to power minus 0.1. The rate will get further reduced that. So this was the result as a class wise 0 to on KMC data set. If you see 0, 1, 2, 3 classes, and these are the ResNet, DenseNet, InceptionNet, IRR CNN model, BreastNet 20, and LiverNet what we proposed 0.90 was average, and that for the precision, recall, F1 score, IOU, and then accuracy. IO is not much relevant, but that time we reported, we thought that's not important, but accuracy is most important whenever do classification task. Parameters is if you see that is lower than any other model reported over here, and flops is also lower in our model what we designed. And then this was a TGCA dataset also. So model was giving the best result in both the datasets, and this was the confusion matrix for the 3 class case here, and different models here. This was a confusion matrix on KMC dataset for the 4 classes, right, of the liver net models. This is a computational complexity. You can see that as a graph part. LiberNet model is having the lowest parameter. Then we extended the model by again with the student, right? That's called 2.x model. This model even was much, accuracy has been improved 9.14 on both the data set slightly, and the number of parameters, we have 2 binaries actually, right? One is even more lighter, 27354 models. So this model was here, what is done? This ASPP block get modified, and then here the top plates also get modified a little bit, and this model was again done by the BTech and PhD student as well. So this is my lab here as a first floor is there. Only 2 full-time scholars are there currently. Rest are MTech, BTech are there. And these are the significant project in medical image processing 3 which already completed. These are the glimpses. You can see that outcome of the lab. So this is my GitHub, you can visit and get all the codes are available, right? And also this called renal automatic grading as well. Also Nature got published in 2023. One more is coming of this year as well, one more scientific report. And this was again extension work, got models in the same data set, grading of kidney cancer. These are the few publication only in histopathology images, what we did it in using the AIML deep learning field. Some more are there going on. This not histopathology, rest all are, see, this is a paper got 2025 got published, work done by MTech student, and one more paper, this also got revision. So he has extended this work, so again under revision it coming very soon right now. So as a future directions, yes, still there is a scope for doing a research in the area of histopathology image processing. You can do segmentation, nuclear segmentation, but you can do instant segmentation rather than doing that part. And of course you can get more data set, prostate Indian data set, nobody is there, you can create that. And breast, I did not find anyone Indian data set which are available, right? Kidney, anyway we have released. Liver, kidney we have done, so if someone wants we can share as well, no problem. But prostate yet to, we are in process of procuring the data from the KMC Mangalore as well. Apart from this, you can go for still hand radiograph, X-ray, mammography, CT, MRI, retinal, fusion, always scope of the further doing some research work, right? May not be doing something like you can develop the product as I told you, right? Already some of things try to come up with the best model, make as a complete base API, but it would be good to make as a medical product, software product on mobile based device, right? So once a mobile base, of course you have to go for edge devices, right? You have to go deploy light models, right? So there is a called TensorFlow Lite. So you can, there is a facility, you can convert model, whatever you train model on the that is standard HIBI models, you can convert into TensorFlow Lite. Straightforward, there is a procedures, you can follow that. That Lite model will be running on any embedded devices, edge devices also, right? I hope this would be useful for you guys, right? Now we'll move on the lab. I'll try to demonstrate one experiment, like how to design deep learning models, right, for classification task right now. That I'll take it. How many of already work on that? Can you raise your hand? Okay, so only that takes less number of students have experience. So it will be good. I'll try to do it from the like beginner point of view. Okay, so that you get ready. Yes, Professor.
Could you please comment on the number of parameters, like 200,000 or 500,000?
Yes.
Versus the size of the image coming in 224 by 200.
No. Number of parameters depend on the model part, right? So yesterday, if you remember that, I told you, we can calculate the number of parameters at each layer, right? Say resonate 50, that means it's 50 weighted layer architectures right now, which that reported was 3.57 million parameters, right? So 3.57 million parameters reported, right? How it's coming, right? That means it's a deep model, right? Each layer, like convolution layers, is have the weights, right? Now parameters. So its parameter is nothing, as I told you, f into the depth of the input image into the number of filter plus the number of filter. So parameter due to the convolution operations and the parameter due to the bias, right?
The system has to learn that many parameters from a few tens of samples of...
No. Samples should be always large. Samples should be large. If you have less samples, then you can go for the graph neural networks. Graph neural network is the right options for when you have a small number of samples, right? So basically you can do graph convolution networks, 2D graph convolution network you can design, right? So what will happen here, the graph neural network that won't accept data as image form. So from the data need to convert into in terms of create as a graph, then give it input to as a model part, right? This is not a very straightforward concept. You have to learn and do that could be there, but choice is there, right? Now as a graph convolution networks would be the right options when you have less number of samples. Apart from this, even this you can use liquid neural network, right? Also is for some applications.
When we say number of samples, is it the number of images or the size of the image?
No, number of sample means images. How many number of images you have, right?
Number of pixels doesn't matter.
Number of pixels doesn't matter, right? Number of pixels basically you have to make as a square image. Maybe 224 cross 224 or 256 cross 256, right? That's there. So it won't accept like 1024 cross 1024 data, right? You have to scale down, because why it is there? You will encounter the computational complexity problem, like memory usage, right? Model won't fit it that in memory. That's why you have to scale down the size, right? 256 or 224, right? Cross 224, right? And so on, right? Depend on that. Or 128 cross 128, depend on the how many samples is there, right? Again, that batch size also matters. Okay, fine. So we'll move to the lab. So lab is located in the adjacent building. This only, the annex on the first floor called DSP lab. So we'll move there. We will try to demonstrate another 40 minutes, right?